folks hear me okay? Yeah, sorry about that. I was trying to track my lost baggage and I got carried away. So let's see. Okay, what we have here, we got this, got it. Okay, this looks good. Okay, good morning. So we are changing the topic now. What we're talking about now is machine learning inversions, or how I call them here, neural network inversions, because that's the only aspect of machine learning that I actually know something about and have done something, and I feel at least a little bit comfortable talking to you about. This lecture is going to be a little bit more casual in a sense that I also want to hear what ideas you have and what experiences you have, and we can maybe discuss it and, see what kind of applications and so on we have and you would like to use and so on and so on. I personally really don't have any idea how popular this topic is among other people. What I personally do know is that I'm always worried when I'm talking about it and using it, that people will complain because at least in our community and in general in scientific community, it's still observed very much like something, unscientific, unphysical, and so on and so on. But we can talk and we can, debate about that and discuss. And I think that there are some interesting applications and uses of neural networks in spectropolarimetric inversions. Basically, the plan is that during this first lecture, we talk about some basics, like what are the building blocks of the neural networks, what conceptually they do, what we can use them for, and so on and so on. And in the other part, which is after the coffee break, I'm going to show you some of the papers that came out over the last few years. And as you will see, this is literally a field that is developing over the last 5 years in the term of spectropolarimetric inversions. So you can see what people have done, and maybe you can contribute with some examples of your own or ask some questions, and we can together look at these things. And I'll try to outline advantages and disadvantages of all the different approaches that we can find in the literature today, and we can, discuss what it all means and so on and so on. So feel free to interrupt, to ask questions. I mean, same as always, this is going to be very, very casual and relaxed, right? So what I will try to convince you is that machine learning is not a scam. It's just a family of methods that you choose how to use and how to interpret. And if you overinterpret them, people will make fun of you. If you use them in an optimal and, verifiable way, probably everything is going to be fine and you can do good things. What we're going to be talking about here is neural networks, which are some sort of, for our applications, which means for inversions, they are approximators for mapping. What kind of mapping? Mapping from spectra to atmospheres, right? One function is a spectrum, the other function is atmosphere. So you can think about them as approximators of operators or approximators of functionals or any along these lines. Coding these neural networks is actually very easy. That is probably an obstacle for many people, that you are like, okay, I don't know how to do this. I don't know what are all these things. Do I have to make it on my own? You don't. You have extremely well optimized and tested infrastructure for these things through various, mostly Python packages, but they're also implemented in other languages. And I have the simplest possible example in Google Colab that I sent to Discord this morning. And if we have the time, we can have a look at it. And it's literally just making it more complicated. Much bigger problem is settling on the architecture that you want to use, testing them, verifying them, making sure that they are precise enough, but also not overfit, and convincing other people that this network or this method is really capturing what you want to capture with it. And if you think that they can help in your research, just use them, give it a shot. Try something simple, see if it can work, and then improve further. And it's once you have it in your fingers, as we would say, it's really not that hard. So let's talk a little bit about what is inversion conceptually for us, right? We tried to convince you during this school yesterday, also last week, also all these other days, that in principle, we understand the problem of spectral line formation very well. If I gave you enough time to read all the books and papers, and I gave you model atmosphere, you could calculate almost the spectrum of any line with any physical approximations there. There are some things that we are still not sure about, like, for example, scattering polarization with PRD in multi-level atoms, and these very, very complicated examples like that. But for most of other things, even if it would take you a lot to go through all the differential equations, chemistry, and so on, you would in the end get a spectral line profile. However, the problem that we want to get is that we want to go in the opposite direction. We want to go from the spectrum back to the model atmosphere. That's what inversion is, right? That's what inversion should be, actually. Let's put it that way. And we already know that it cannot quite be that way for many reasons. But mathematically, if I was gonna depict how a forward problem looks like, I would depict it like something like this. Can I have a pointer, please? Somewhere around, but it's maybe in the back. Yeah. Yeah, no worries. All good. Do you also have the? Okay, so this is how I would depict it. Like you have a functions, temperature, pressure, velocity, magnetic field, which depend on Z, on the height of the atmosphere, right? There is a complicated process that maps these functions to a different function in different space. We're not in space of Z anymore, we're in space of lambda anymore. And I hate saying this, but I was listening to one of the first lectures by David, and he said, oh, wow, it's a miracle that Milne-Eddington needs 9 parameters, and for regular line formation, we need 5 parameters. I strongly disagree with that. In normal line formation, we need infinite parameters because these are functions, these are not values, right? In principle, this can have infinite resolution along Z. That is unknown. The problem is that we can't constrain it with the infinite resolution, so we reduce it, right? But when you're doing LT inversions using SIR or Desire or Stick or anything like that, you are inferring a depth-dependent structure, which is a function that's significantly different than inferring a parameter. Okay, so that's one clarification that I wanted to make. And this here cannot be written analytically, unless in some very, very simple examples. For Milne-Eddington model atmosphere, this can be written analytically. But for example, already for LTE problem, it cannot. Why? Because in the process of LTE solution, there is something hiding that we simply cannot write down simply. One thing that we didn't talk about at all, but is actually the most complicated part of most LTE codes, is solving the so-called chemical equilibrium. What is that? I give you pressure, I give you temperature, and you need to solve the equation of state for all the species and their ionization stages and their excitation stages and so on and so on. And that's a big pain in the neck. And that's why people just pass one, Uppsala opacity package from, through the generations and so on and so on. At some point, we won't be able to compile it anymore, right? All these things hide in this function here. And now we want to actually functional or operator. And now we want to find the inverse of that operator, right? And it's really ill-posed by the definition, this problem, right? And I can very easily convince you of that if I tell you, take, full atmospheric model from the deep photosphere to the corona. You can calculate Hinode lines from that easily, right? But can you infer the structure of the corona from Hinode lines? No, you cannot. So the inversions are doomed to fail, and we, at the beginning, need to restrict ourselves to a given range of heights, a different complexity of the atmosphere, and so on and so on. Additional thing is that simply inferring these full stratification of these functions is pretty much impossible. So that's why we decrease the number of parameters through various techniques. One technique, I don't know if it was immediately obvious to you, but for example, pressure is an essential physical quantity in calculating the spectrum, yet we never infer the pressure. Pressure is eliminated by assuming something called hydrostatic equilibrium, because people found that allowing pressure to be a free parameter would simply result in ridiculous solutions. The other thing that people found out is that you can't really treat every point in your discretized atmosphere as an independent variable, because their effect on the spectrum is too similar. So we need to shrink that using these so-called nodes, right? And that's why I often like to take these functions of t, p, z, and so on, and merge them all in some parameter, capital theta, right? And you can think about this theta, this can be a set of Milne-Eddington parameters, this can be values of your nodes, of your maybe constant microturbulence, microturbulence, and so on and so on. So now the intensity kind of becomes a vector function, okay? It takes all these individual values And we can have few of them, or we can have many of them, 20, 30, 50, as Carlos said, right? He said, like, take 50 nodes or something like that. And that function will map this into a vector quantity here, which is your polarized intensity. And then we fit this. As you have heard first week, we fit this, and we usually use something like this to drive this fitting. We find the derivative of this function with respect to each of these individual parameters, and we use it to drive our minimization algorithm. For example, Levenberg-Marquardt or something like that. These are not the only examples of this. For example, Hazel, that you will work with tomorrow, for a good part of its fitting, it uses parameter search. There are genetic algorithms they can fit. There is a simplex method that you can use to fit. You can, in principle, this part can be done in any other way. You can use Markov chain Monte Carlo if you prefer, and if you are faster, right? And the inversions, even though they're beautiful and we talk about them all the time, and we teach you how to use them, they have a lot of problems. One problem that we know is the insensitivity, right? And we talked a little bit about it, and I gave you this example before. Sometimes some physical parameters of the atmosphere are just not well constrained by the data. What does it mean? It means that if I change this parameter even by a lot, spectrum doesn't change at all. This is also what response functions are telling. Then we have degeneracy. Degeneracy means different combinations of the parameters give same result. Now, today, when we work with Hazel, we will see that there is specific time of degeneracies that are called ambiguities. Ambiguity means through the equations, you simply see from the equations that different values give exactly the same result. Simply equations tell you that, like you have cosine 2 phi. It means that phi of, pi and phi of 2 pi give the same result. However, there are also ambiguities that are simply there because we don't see things in infinitely precise way. For example, okay, I'm going too specific, but it turns out that if you invert Hinode data, there are different photospheric temperatures that will, in combination with other temperatures, give you the same continuum intensity. That is unsettling, right? We think that continuum is tightly related to the photospheric temperature, right? And plus, there are some of these things here that I also like to mention from time to time, and it's inversions are great, but there is simply a lot of obstacles here, and maybe the most practically important for us is that they're numerically very demanding. You take, for example, even very fast inversion, like a desire inversion, which lasts a couple of seconds, but you have an observation that has few million spectra, which WISP and VTF especially, the deakest instruments, will deliver to us. You can calculate right now that it will take you days, weeks, months to invert that data. Then you find a mistake, and you're like, hey, I have to do that again. And it's not a problem just of your personal time. It's also a problem of spending money on the electricity, heating up the nature, producing all these things, and so on, wasting somebody else's time, and so on. But there is a lot of things here to advance, and through the time, people came to alternative ideas, which do not rely. And what I want you to notice right now, the biggest, no matter what you use to drive your fitting, thing that takes the most time is you're calculating your spectrum again and again and again and again. And I think you are already feeling here that a lot of the time is wasted. For example, when you look at Hinode data, when you look at any quiet sun data, actually, so many pixels are so similar. You're like, man, I probably calculated this pixel as an iteration of some other pixel at some other moment. I'm wasting so much time doing this again. And machine learning methods in general, not only neural networks, are some way to maybe go around these things and simplify them and make them more time efficient and more. And today we're going to be talking about it. Okay, enough with the depressing things. If you told me to summarize what neural network inversions are and how they work, well, they basically aim to interpret the spectra by learning this. And I put on purpose inverse here in parentheses because there are classes of these called invertible neural networks that learn both ways. But we're trying to learn this mapping from the spectra to physical parameters, or from physical parameters to the spectra. And what I want to emphasize is that it's from some good training set. It's very good to make precise. It's very easy to make precise neural networks. What is hard is to make such a training set that you are convinced that that neural network is doing a good job. And I think that none of us is convinced, even when we publish a paper and everything, we are still not convinced that it couldn't be done more general and more easy. And again, if you ask me to describe a neural network, basically, I would say it's kind of pipeline. There is an input, which is some sort of vector. By vector, I mean series of numbers, for example, image, spectrum, something else, I don't know, time series, something like that. Then there is a lot of things happening in between that are hidden from us, and they're conveniently called hidden layers. And then there is some sort of output, and that output can be one number, for example, velocity, field, can be few numbers, for example, Milne-Eddington parameters. It can be the whole function, for example, atmospheric structure, something like that, right? And there is some sort of flexible machinery here in between, and we'll be talking about this flexible machinery. These are called layers or neurons, or things like that. And that machinery is tuned, and this tuned, it has double meaning. In one way, it's tuned that we are tuning it. We are changing their order, their size, their type, their activation, and so on. But also in the process of training, in the process of learning, the network, the machinery, the package that you are using is tuning the parameters, the numbers behind this machinery, so that it reproduces, that it works well on your training set here. And today we will maybe have the time to see how it exactly works. And typically that machinery is individually very simple. You have some very basic operations, matrix multiplication, you have convolution, you have very important thing today, which is called nonlinear activations, which are basically very simple nonlinear functions that you apply to these intermediate results that, when repeated many, many times through many, many layers, allow you to mimic very complicated nonlinear functions, right? And the training is basically iterative adjustment of these, parameters here. We will have example later that allows you to learn your training set well, and you hope to generalize later. And it's really up to you to scrutinize that after that. So after you have, trained the network, it's up to you to come up with robust, strict, tricky tests to really see if that's doing a job or is giving you some nonsense. I will give you an example of some nonsenses. And for that, I will use but also I think probably the simplest approach to neural network inversions today, which is basically what we call mimicking regular inversions. And we simply took some amount of data from simulated quiet sun, inverted it to find some small, modest subset of parameters. And then we trained the neural network to map these spectra to these parameters and simply apply the network to the other unseen data. And we hoped that it will work on any data set. Now, what do I mean by any data set? Not literally any data set, of course. What I mean here is we hope that it will work on data sets that are similar to it in actually many ways. First of all, if you train your network on some specific spectral line, you can only use it on that specific spectral line. Not only on that specific spectral line, but also on that specific spectral line observed with the same wavelength sampling, with the same spectral resolution, with the same instrumental effects. Noise might prove to be important, maybe not that critical, but should be similar amount, and so on and so on. For example, you cannot train your network on IBIS data and then apply it to Hinode data. It's probably not going to work, even if the same line is in question. At least not with these basic networks like that. Probably today we have much more complicated things behind. Your normalization, your preparation of the data has to be the same. And also the things that you're seeing in your data needs to be the same. For example, I cannot take quiet sun data and train my network on the quiet sun and then apply it to the sunspot. It's not going to work because it's suddenly going to see very strong magnetic fields that are not there, and it's not going to work. If we go to a little bit nitty-gritty details, I probably shouldn't take a network, train it on very poor spatial resolution data, and then apply it to very high spatial resolution data, because all weird, asymmetric, line profiles and so on are going to appear there with much more narrow lines and so on and so on. My network is gonna get confused, right? So in principle, and also, like, if you change between different sets of data, you might wanna not only retrain your network and readjust these parameters that are hiding behind, you might want to actually change the architecture and the concepts behind it. I will talk more about this specific paper and these results in a second part of the talk. Right now, I just wanted to show a little bit more what is actually happening here. So in these specific examples, what we take is we take a pixel out of our observations. And as you know by now, that pixel is actually a spectrum. Spectrum, it's a polarized spectrum, right? Here you see that spectrum is very wild because it has a strong magnetic field and lines that are split. These are infrared iron lines that I don't think we talked about them a lot in this school, but these are very deep photospheric lines, very sensitive to the magnetic field, so very good for that. And then we formulate them as some sort of vectors, right? There is a series of numbers describing Stokes I and the series of numbers describing Stokes V. And we treat them here as channels. What are channels? So channels are, for example, equivalent to colors when you talk about images. Like you have R channel, B channel, G channel, and so on and so on. And then these channels go through a series of operations. Here we use something called convolutional neural network. Convolution mixes the information between these things here, and is typically used with these pooling layers. What are pooling doing? Well, they are essentially binning things. And then we process it further. We eventually reach something called dense layer. So what are dense layers? Where these are the layers that are mixing information completely behind. And eventually, when we stack all these things up, at the end, we have the output of the model parameters. And for us, the model parameters were these famous nodes, right? There was what temperature in first node, second, third, fourth, blah, blah, velocity, magnetic field, and so on. And so what do I do when I set this up? Well, I set this up by having some known data here as the input, having some corresponding nodes that I know, that I trust, that I know the correct answer for. And then all the numbers that you don't see now, but you're going to see them soon, in between are tuned to kind of fit this, mapping between these two things. And actually, I have a much more simple example how all that works. And it is this, right? This would be the simplest possible neural network, right? If I have a linear function here, and actually, I don't know if it's a linear function. I have some data here, right? And I could try to learn the mapping between these data here. And I could say, well, the simplest thing that I can try is just a linear function, right? In a way, this linear function is something called function approximate. We don't know what function is behind these blue points. Maybe there is a very complicated, oscillatory function in between, or some high degree polynomial or something like that. I don't know that. But I'm choosing here to try and approximate this data with the line. And keep in mind, technically, this is a fit, but I'm not really fitting it, in the sense that when I say fitting, I want to talk, I imply something else. And during this school, you talked about the inversions, and I will outright say that inversions are just model fitting approaches. And what is for you model fitting? Or if you don't want to tell me that, try to tell me why I'm so hung up on making the difference between fitting and the neural networks. What is for you fitting? When I tell you fit this, what do you typically need to have? Fit the model to the data. Go ahead, Josh. I need an objective function to minimize, and that objective function, which is good, which is true. But in science, when we fit something, what is usually our motivation? A model, exactly. So we typically try to have something called generative model. And by generative model, I generally imply that that's something that is motivated by your physics. For example, generative model for SIR is LT equation of state combined with Zeeman effect combined with the numerical solution of radiative transfer equation. It's a very complicated model, but it's justifiable. And then I do model fitting, and then I fit, and then I know that I'm ascribing, that my temperature has physical meaning, right? For example, much more simple example is doing a simple pendulum experiment, and you want to determine G, right? You know that square of period is proportional to the length of the pendulum. You draw this, you draw a straight line. That straight line is motivated. The parameter of that straight line is a physical parameter that you want to find. You're really fitting a generative model to the observed data, right? And typically we will show it something like this. There is a function which is generative model. acting on your independent variable with given parameters, and then there is some noise that is distributed in Poissonian way or Gaussian way or something like that, right? Okay, but what I did here is I didn't tell you what this is. I didn't tell you whether there's motivation for this straight line. I just drew the straight line here, and I used the fitting concepts. I minimized some chi-square or whatever, but I didn't have any physical motivation. So why would I fit something without a physical motivation? Do you have an idea? There are also reasons to do that. What could be my motivation for this? I want to, for example, interpolate my data. Right? We will often fit things with polynomials or splines or things like that without any physical motivation, just because we want to interpolate to get something. Or maybe I want to see the trends in my data. I want to see how much dimensions it has, right? When I do this, I see that there is some scatter around, but I see that basically my data is more or less one-dimensional. And I see that the most important dimension is its variation along these axes here, and less important dimension is the scatter around this axis. This is what this famous PCA would tell you. PCA is finding the principal directions in your data. Here there is one direction, which is more important, the other direction, which is less important. I maybe want to compress the data, right? How do I compress the data? Well, I say, okay, this around here is some noise. Essentially, my data is in the line. And you can do that with spectra, for example. You can PCA compress the spectra by, finding some components and then only keeping small fraction of these components, and that will remove the noise because the noise is random. It doesn't get captured by the low order approximations, right? So on and so on. And this is basically, in a way, what your machine learning methods, these simple machine learning neural network methods are doing. They're approximating this function with something that we hope is robust, generalizable, and precise, right? So if this was a little bit different, maybe we would have chosen square function, third-degree polynomial, sine, cosine, maybe something else, and so on. But that's the main topic. I have many examples. From these examples, I learned some complicated mapping. Keep in mind that this is just one-dimensional input and one-dimensional output. For neural networks, we can have multi-dimensional inputs, multi-dimensional outputs. Actually, technically, this is zero-dimensional, right? Because there is only one value as the input and one as the output. For example, if you input spectra, that would be one-dimensional input because it's an array of numbers. You output the atmospheres, one-dimensional output. So, right. And in principle, neural networks can have, thanks to this stacking of these operations that we still didn't talk about specifically what they are, they can have much higher flexibility, right? And in this case, you see an example of that. Like I have an input that is 6 numbers. What can 6 numbers be? Well, for example, HMI spectrum is 6 numbers, right? 6 points. And then I pull it through some thingies here, some operations. In this case, they all look like densely connected layers. And I have here in this, I just took this from the internet. I didn't make this for my own example. So here you have two values of the output, for example, velocity and, I don't know, continuum intensity, let's say, because here we had only stock size, the input. Here we have two. The operations in between, they have nothing to do with the physics of spectral line formation, right? But they are, it turns out that these, matrix multiplication, addition, nonlinear activation, convolution, all these things that are happening here, they're powerful enough, they're flexible enough that they capture your trends in the same way that this straight line captures a trend in this data here. So this is this cheating? Well, maybe it's cheating, right? It depends. It's really up to you to say. Some people will say, yeah, I'm not interested in that. There is no physics inside. Okay, I'll speak a little bit later about ways to add physics, to enforce physics in the neural network, which requires much more complicated architecture than this one here. But in principle, if you trust that your mapping is robust, that your training set is good, the way to verify that, well, why wouldn't you trust it in the end, right? It saves you a lot of time and it creates small, if any, errors. And if these errors are just due to the random noise, then things are fine, right? So in principle, we can hope. Here is a little bit more complicated example. Here are the depth certifications of temperature, pressure, right? the total number of particles, magnetic field and the velocity taken from a Bifrost cube, right? And what I calculated here is the sodium D line and neighboring photospheric lines, and then Stokes V for all these. And you see that they're not like super exciting, even though the depth variations here are wild, right? So always keep in mind that it's very easy to go from this to this. Very hard to go the opposite way. Like here, if I inverted this, I could hope for some, reliable estimation of these parameters in some range of heights. Not really, I couldn't ever hope to retrieve my full depth stratification like this. Right. And now a little bit about the commonly seen examples. I think a big problem for all of us when we want to use neural networks is that we go online, there are millions of examples. They're all tied to something that has nothing to do with inversions. They're all related to, for example, images. And this is the most basic problem that you can use to, to basically learn coding in the neural networks, where people take image, they put that image through a lot of various convolution layers. In this case, eventually they put it through some more operations and they have the output. What I want you to pay attention to here is the output. Output is 10 fields. And in principle, the one which on the training set, the one which corresponds to your input number will have value 1, the other ones will have value 0. Then you will train your neural network to recognize this. And when you input a random digit here, some new unseen one, what you will get here is a series of small numbers and a really large number, the number close to 1 for the number that network thinks the input is, right? And in that way, this classification scheme, like the one that we often see here, is really not different than what we would call a regression scheme, which is what we want for inversions, right? For inversions, we get the output of the function and we care about the every value. Here, we just care which value is the highest, which is the one which corresponds to, the most probable digit being input, or you go and you see something like this, right? The neural networks that are trying to decide whether something is a muffin or it's a dog face or a cat face, or so on and so on. So most of the examples are like that, and that's a little bit annoying for us because it's a format that we are not working with. We're not working with images in this case. We're working with spectra, or maybe spectral cubes or something like that. And typically, most examples are also not regression examples. They're classification examples or generation examples. What does it mean, generation examples? People try to make neural networks to find how the hidden parameters of the data are distributed and how they look like, so that by finding their own combinations of these parameters, they can create plausible outputs that correspond to the inputs. For example, I give a network a lot of examples of the faces. We find some hidden representation of these faces. I have an example for that later. And then from that hidden representation, which can generate new faces, which look completely, plausible. So these are very magical things, and you can do that from spectra, for the spectra too, if you want. Right. Okay. And in principle, what I was just saying here very briefly is that so-called classification problems, which you typically encounter online, are very similar to regression problems, at least for something called supervised learning. What is supervised learning? It's when I know the answer, right? I know this is the input for the spectra, these are the output parameters, that's what I want to learn. And I give my network a set of data and it learns on that, and that's it. Or we teach it on that. There is also a class of methods which is called unsupervised learning, and which is also very powerful and very good. And I never use it, and I don't know much about this, but this one example that I know of is pretty much like inferring something while having the network do something else. For example, I take a lot of images of the sun, and I teach my network to compress them, but through the compression, I achieve, for example, classification, because in the compressed space, the things are separated. They're separated, for example, this is the coronal hole, this is the, active region, this is the quiet zone, and so on. We are not telling it what the correct answers are. The network reaches these, what we want as a kind of misproduct of what it's already doing. So now a regular question for all of you would be, okay, I hear that these things are cool, that they're interesting. How do I make a network? The easiest is you just sit and try. Maybe you read a couple of papers to just kind of be prepared of what kind of architecture you should go to. It's really not that hard. So what we're going to do now, before we go to some examples of recent works, we're going to talk a little bit about what are these most well-known layers or ingredients of the neural net, right? And in principle, the neural network is most of the time, for some basic approaches, a very simple linear neural network. I don't know if linear is the correct word, but the one which just simply works as a pipeline. Like I make one product, then the next layer turns it into something else, and so on and so on. Eventually, what you will learn about is that there are also things called skip connections, which are skipping over some part of the network to kind of create a different connections between your intermediate products. And it turns out that these skip connections are very powerful and that they help you a lot with training your network, right? But in principle, what you can achieve, if you want, for example, to repeat what Ricardo and me did, is you can just combine these two types of layers, linear or dense layers and convolution layers. And then you combine them with something called activation function. Activation function, because both these operations are linear. Convolution is a linear operation, just a linear. What does it mean, linear operation? It means that the product in this layer here is some linear combinations of things here. Same thing here for this one. This is just a matrix multiplication. We'll see examples soon, plus some constant on top. So it's linear, right? Then you typically, after you apply this, you add something, some activation function. And people, I don't think they originally treated that in like 90s and 2000s when these things were first time created. They recently figured the activation functions, and activation functions allow you to capture nonlinear behavior in your data. And then you complement it with some, auxiliary operations like pooling, which means binning, upscaling, which means anti-binning, reshaping, and so on and so on. Right? Good. And this is what neural networks were for a while. They were consisting of these linear layers. So I have some input, and I create the other input by multiplying it with some matrix and adding some constant here. And these are called weights and biases. This is the most typical way how you will find them called. So I have input of 5. I have a linear combination between all of these, and then I add the bias. And at the beginning, the values, these weights and biases, are going to be random numbers. But eventually, they will adjust the training process so that they best reproduce your, input data, so that they best reproduce your output data for the given input data. So for the moment, just imagine that there is nothing but this one layer. So Y is input, X is the output. Let's say, for example, these are the 5 points now in some filter graph measurement in Stokes V, let's say, and these are the magnetic field. These are, for example, velocity, magnetic field, and let's say inclination or something. Or no, let's actually make it even more interesting. Let's say these are magnetic field, inclination, and azimuth. Probably the connections toward the azimuth and the inclination are going to be very weak or non-existent or random, simply because Stokes V cannot infer these two things. But the connections toward the your magnetic field here are going to be strong, and the points that are more important for determination Stokes V are going to have more important connection, or better constraint. Right. So here is a little question for you. Let's say that we have a single layer and we input the Hinode spectrum. I don't know if you see a single Hinode spectrum during this. I hope we did in the school. This is an example Hinode spectrum here. The spectrum has 112 points. This is a continuum here. Let's say that I want this, spectrum to go through a single dense layer, and I want to find depths of these two lines and their positions as the output. Okay, so I have 4 outputs in total. How many free parameters does this network have? I give you a few minutes to think about this while I go and grab. Input is 112, output is 4, and I have 1 dense layer. To remind you, W is matrix, B is a vector. Anybody has an answer? $452. Yes, I think so. So it should be, well, let's see how we reach that number. So this takes an input of 112, produces 4, so it should be 4 times 112 matrix. Do we agree? And then this bias needs to have the same dimension as y. So these are all vectors and matrices, okay? Even though I'm writing them as numbers. So this bias needs to have dimension 4. Let's see if I have. Yeah, 452. 412 matrix and 4 biases. So our function approximator, or our pipeline, or our neural network has this number of free parameters. And you're like, wow, Ivan, are you insane? 452 free parameters to approximate 4 numbers. Something is wrong there, right? There should be a simple way to do that. But think about it like this. 452 parameters to describe all Hinode data, to describe line depths and line positions of all Hinode data ever recorded, provided that our training set is satisfactory, right? And that our neural network can work, So in a way, we are approximating all the possible data that we expect to encounter with this one given neural network and its parameters that we have found. That's very powerful, right? In a way, that's like I put all my physics, I put all my data in this one neural network model that is trained, and it takes few megabytes. Here it would take not even a kilobyte. Okay, now I can add 2 layers, right? I could say I have 1 layer. Of course, this is again some random example. It's not a network that I made for this, but let's say I could go from 112 to 20 points to shrink it and then shrink it further to 4. Now this would be much, much more, right? I don't know if I calculated it. I did. The first layer would be 20 times 112 matrix plus 20 biases to get this number. Second layer would be 4 times 20, right? Because I have 20 input plus 4 biases, 84. So it's 2,300 free parameters. This network is much more complicated. It has much more free parameters that I need to learn, but it's also going to be much more powerful, much more flexible, much more precise. And then we can keep doing this. And this is what we call today deep learning or deep neural networks. What does deep mean? It's not deep in the sense that it's very complicated or hard to understand. It's deep because I've stacked a lot of layers. And we didn't do that before because we didn't have powerful enough computers and flexible enough architectures to do that. And the more complex the network is, the more precise we expect it to have. And in principle, we could do that until we get the perfect fit, but that doesn't mean that our network is good. Because if I do this in more complicated way, in the end, my network is going to literally learn my training set. By literally learn, I mean it will literally say, okay, spectrum number blah blah has these blah blah numbers exactly, and then this has this one, and this has this one, and so on. And in real life, it would be like this. I teach you how to make, for example, one type of pasta. Okay, one type of pasta dish. And then instead of going and buying the Checo, we buy Barilla pasta, and you suddenly don't know how to make it. That's not learning, right? I overtrained you. You only know how to do this one very, very specific task. And it's not good. It's not generalizable, right? So we want, let's go back to this example here. We want something that is not overfitting, right? This is overfitting. This is going through these lines here. But then if I give it next point, instead of it being here, it can explode and go up here somewhere or something like that. And this is also not very good because you see, it's not reproducing, not even the data that we have. This is maybe something that you want the most. The problem is, and I think this is the reason why people hate machine learning so much, is that there is no objective way to find this neural network architecture, this function that does good. There is no way to say, oh, this is the physics, and then I just do that. And then, for example, Han comes and tells you, you don't need PRD for calcium 8542, and you go and you disable PRD, and now your model is simple. And then Carlos comes and tells you, you don't need 17 nodes to fit node lines, and you go and you put 3 nodes, and then your model is more simple. You have something of, but these things are also kind of personal, right? The nodes, why are nodes polynomials? Why are they not Legendre polynomials? Why are they not sinusoidals? Why are we not working in Fourier space, and so on and so on? Okay. And obviously, we don't want that. We want some optimum, so our network is precise, but it also generalizes well, and we want to be somewhere in between. And this is when we are supposed to stop. I'm just going to tell you what convolution layers are, and we're gonna stop. And convolution layers are a great way for you to have powerful features in your network, but at very low cost in terms of parameters. Why is it so? Well, let's say I want to shrink this 5x5 matrix in my neural network to a smaller matrix. I could do that by having dense connections, but there's going to be a lot of these dense connections, right? It's going to be 25 times, what is this, 9? That's already a lot of numbers. Instead, I can use something called convolution layer. What is a convolution layer? Well, okay, sorry. I was supposed to point to this one, not to this one. This is the so-called kernel. Convolution layer is a kernel where these numbers here are unknown. I'm also training for these numbers, but it's same for every part of this input here. So I'm gliding this kernel over the input and I'm getting some out. So I'm shrinking my input here. I'm decreasing it. Technical term, what people in machine learning like to call is I'm extracting features, but at very low cost. I only have 9 unknown numbers. And when people figured that and tried this, they found out that these things work extremely well in image processing and so on. And because they conceptually seem to reproduce, seem to play the role of extractors for features, and these convolutional layers play the roles of so-called feature maps. And by feature maps, you could, what I like to imagine from our standard image processing and data processing techniques are like filters. For example, if I want to find, what we talk about? We talked about fibrils, right? If I want to find fibrils in my image, I maybe want to apply some sharpen mask, some gradient filter, something like that, and I will get where my fibrils are. Instead, I can just give my neural network image with fibrils as the input. I can give examples of what we already did and where we recognize the fibrils with zeros and ones, and network will, in this process here, kind of find its own filters in terms of these convolutional layers and fit maybe even fit the parameters of these convolutional layers to correspond some known filters, and we'll get some sort of useful input. And in this case, people have example on this, image recognition, where you take an image of an animal, and then successive convolutional layers are extracting some features. What are features? For example, head is this big. Gradient between ears and this is this big. Colors are distributed in such a way you don't even know, it's kind of abstract, and then it comes out here as probabilities of what you're looking at. Right. And then to make it all even more flexible, you add these activation functions. What are activation functions? They're a way for us to add nonlinearity. And typically these are very simple examples here where you have one input and one output. And they are all something like this, something with a huge gradient at some point and a small gradient out of here. And now you could say, oh man, how can this be powerful? This is not powerful, right? This is I just input one number, I get the other number, and it's most of the time either 0 or 1. But it turns out that when I stack this, when I apply this to many components of my vector, and then I stack them with the other ones, they can mimic any function that you want. Right? Very complicated, very non-linear thing. And that way we can create stuff, right? And before we finish, I just want to talk about something called autoencoders. Autoencoders are neural networks that have the same input and the output. And now you might want to say, oh, Ivan, why do you want that? Well, I maybe want that because I construct my neural network in such a way so that it, for example, decreases, which is what we call encoding. The dimension of the vector decreases, which I call encoding, and then it increases here, which I call decode. And that way, I'm basically developing a network that is compressing my data. Why do I want to compress data? Well, most of the time when we say compressing, we think, oh, you're compressing music because you want to put more music on your phone, or compressing images so they take less space, and compressing space data so that we'll reach Earth faster. But compression is a process of actually finding important features in your data. When I compress something, for example, using PCA, I'm finding out which PCA components are most important for my data. When I compress image, I find which things are the most important, right? We also unconsciously compress things. when you remember me, you won't be like, oh, he had a pixel here of this color, pixel here of this color, pixel. You will be the tall guy which shouts a lot, and his baggage got lost, and he was complaining all the time. Like very small number of vectors to describe that so that you can remember. So this is what the autoencoders will do. And here is what I just wanted to say about the generative networks is that you can make these autoencoders in such a way that these unknowns here, this compressed space is some distribution, some Gaussian distribution. And then you know that, and typically we call it latent distribution. Why latent? Because we don't see it, it's hidden from us. It's something that network infers from the given data. But then if you make it so that this distribution here is normal, then you just draw samples from this normal distribution, decode them, and you get feasible things. And this way you can generate images of people, you can generate images of solar granulation, you can generate whatever you want. And yeah, they're interesting. The autoencoders are very interesting. And later we'll see an example of a neural network that is made by using encoder for one part and then decoder, which is different decoder, so that you get something else. Okay, good. Yeah, I don't want to talk now anymore. I suggest we make a break, and then we'll go through some important machine learning slash actually neural network papers that appeared over the last years. And yeah, I will leave you with this slide where we have some properties of neural networks which give it advantages and disadvantages. And also, before we continue, they can be used for more in solar physics than just inversions. They can be used for inferring temperatures, so velocities, so basically tracking, image restoration, mapping, super resolution, stuff like that. I didn't talk at all about something called backpropagation. Backpropagation is a technical element of your training, which I don't think is important for us right now. This is something that your infrastructure does for you. And when you encounter in the problems in training, then you will think about backpropagation and see why that can be a trouble. But there is no reason for us right now to talk about that. So I will leave this slide here. If you have any questions, you can go now. If not, we can continue at 9:45. We're all mine all day today, so we will shuffle these things around. But yeah, I'll say little break. Any questions now? So
quickly, Ivan, throughout this conversation, been focusing on static things like one image or through wavelength, stuff like that. I'm curious about, since really like most of these things are evolving in time, then what is the difficulty or do these networks have difficulty in reproducing this like time evolution?
Great question. I don't, for the most general case that you probably are thinking of, which is like simulation in terms that it's series of cubes in time, I don't know. That is a huge amount of data, even larger than people usually have. But in principle, they can be used for time series because time is just a coordinate and anything. So I could, in principle, give my neural network a light curve and ask for parameters of the exoplanet or binary star system or something like that. Or I could give it even light curve of flare and ask for input energy or something like that. Right, let's have some coffee, some snack, and so on, and we meet here in 12 minutes. Something a little bit different. Instead of talking about these abstract things and so on, we're going to look at some examples, and then if the time permits, we're gonna look at one. We're gonna look at examples from the published papers and their results and concepts. But then, if the time permits, we'll look at the very simple way how to start writing your own neural network. Just so that you all kind of know what's the plan for today, at least until lunch. Now is 9:45. We're gonna go until 10:40. Then we're gonna make break until 11, so that we can go from 11 to 11:55 as intended, and then we go for lunch. And then after lunch, we proceed as it was planned. And after this 20-minute break, we're going for Hazel. So we are completely changing not gears, but the car, right? Okay, good. Okay, so we talked about this, and actually the first examples of neural network applications were already at the beginning of 2000s. The first one was by Thorsten Carroll, and a few years later by Hector Socas Navarro, who, by the way, maybe at this time was working here. I don't know. Basically, the point here was they probably, people were already using neural networks back then. And what we need to know, and what is good for us to know, is that neural networks are not only studied because they're applications, they are used to model things. And originally, the reason why they are called neural networks is because they were made to mimic how people thought of neurons in the brain. So even today, you have psychologists who are training neural networks with the goal of understanding how human brain works, right? So what you have here, what these people did is they had some training sets with some typical model parameters. In this case, it was field strength in the photosphere. What they would typically do is they would create some training set by taking existing atmospheric models and perturbing them. You didn't have sophisticated simulations back then, right? You didn't have like Muram simulation that reproduces all the observables of the quiet sun to a very high degree. You had HSRA, FAL-C, few more models, I don't know, Holdmuller or whatever is the name of the model, and then you take these, you jumble them up a little bit, you change the magnetic field, change the inclination of magnetic field, change the velocity, pump the temperature a little bit up or down at different heights. You get some training set from that, you train your neural network, and then you ask it to infer some parameters. And this is from the paper of Hector Socas Navarro. You have a sunspot here. This is the map of the magnetic field, and this is comparison between artificial neural network. They were called back then artificial neural networks, right? So the output of the neural network versus the magnetic field inferred by Milne-Eddington model, right? And you get that it has some reasonable agreement. Today, we can probably do much better. But already, if I showed you this and told you this is a magnetic field of a sunspot, you would buy it. You would be like, okay, it's a little bit ugly, but it makes sense. All the things are there. Like there is no nonsensical parameters here, right? So already back then, people knew how to make these. The problem was that computers were not so fast, so training would take a lot, and most of the people were writing their own neural networks. I don't know, maybe MATLAB or IDL eventually had some, features for that, but it was not until, people who were developing things like TensorFlow, PyTorch, and so on, started developing these super powerful, super flexible, very well optimized frameworks in Python that also work very well with MPI, that works great with the graphical processing units, and so on. So I'm going to go through this paper, not because it's first, actually through these papers, because they all use very similar concepts. Not because they were first, but because they use the simplest possible approach to neural network inversions that you can come up with. And that is, hey, let me take some existing database, or let me create a database of already inverted atmospheres, and let me train a neural network on that, and then apply it to the rest of the data. For example, how could you do that? You could, for example, go right now to, we are even at HAO, so that's very nice. You can go to, Hinode database, download a couple of maps, download the input data, which is the Stokes, but also download something called level 2 data, which is Milne-Eddington inversions, and then train a neural network to map between these two and invert all the existing Hinode data using them, right? Start that project right now, and it won't take you so much time. So this is what was done in these papers here. Me and Ricardo were working on synthetic data. Then again, me and Ricardo and some other people were working on various examples of observed data. Alberto was working on iris data. These two papers have polarimetry. This doesn't have polarimetry because iris doesn't have polarimetry. But the concept everywhere is pretty much the same, right? You take individual spectra, you subject it to some torture, it spits out the atmosphere. And the advantages of these methods, there are many of them. First of all, it's very easy to verify, right? Why? How is it easy to verify? Because you can take normal inversion, do exactly the same thing, and you get very comparable results to each other. You can see, okay, I'm doing good, I'm not doing good, right? You can also, in principle, you should be able to take your resulting atmosphere, synthesize it back through your model. In iris, that's stick code. For our case, it was SIR code or something like that. And then you can compare and see, okay, my neural network is doing a good job. One thing that I didn't talk about that is kind of, specific for inversions, and why I think people are cautious about machine learning when you talk about inversions, is that this regression process, the process of going from the observations to the inferred parameters, it doesn't enforce anywhere the forward problem, right? It never ever forces your actual output to reproduce in terms of formal solution of radiative transfer and so on the input, right? The network is taking these examples of input, examples of the output, and learning the mapping in between, but there is never radiative transfer equation in there. So you are not guaranteed that your result, when fed back into SIR or RH or whatever, will give you back the original spectrum. And that's what people don't like. In these approaches that I talked about here, typically you get very good fits because you're literally training on the examples of already performed inversions. And the output is very simple. It's easy to compare. The network is unlikely to pick up outside knowledge. What does that mean? It means that you are not bringing any other information in there except what your inversion would already tell you. It's not maybe obvious to you what other kind of knowledge we could bring in, but when I show you later examples of networks trained on simulations, you will see what I mean, right? And typically these networks are simple in the architecture. And if they're simple in the architecture, it means that they train fast, that they are robust to train, and they typically work insanely fast. And by insanely fast, I mean really insanely fast. Not seconds, not parts of the second, parts of a millisecond. Just keep in mind that the only thing that your network needs to do once it's trained is to do few convolutions, few matrix multiplications on the one-dimensional data and spit out this. And it's doing it through a highly optimized, pipeline package and machinery that was written not by somebody who has PhD in solar physics and then was forced to write it. It was written by a computer science engineer. And it's optimized, robust, and going very, very fast. And what we found here, for example, is that this whole process takes 10 to the minus 5 seconds, where you invert the whole map in a few seconds, which is not something that you can get with anything else. Right. And it's especially important in these examples here, because if you want to invert iris data, there are two magnesium lines, H and K, which are highly non-LTE, PRD lines, and even with desire code or something like that uses some tricks to go fast, you'll probably need minutes to fit one spectrum here. If you spend 1 minute on one pixel and you have thousands times thousands, I don't know exactly what size of the iris slit is, you're not getting there very fast, right? So what Alberto did here is he had some examples of stick inversions. He trained on these specific things, and then he made this deep iris. Here you can, for the moment, we're not going to talk now about the middle picture. It's using some intermediate approach, but here we have a field inverted. So this is temperature at log tau -4. So this is already lower chromosphere. Here we have what stick inversion code. We didn't talk about stick inversion code in this school, but it's a very powerful inversion code, also very numerically demanding, which is literally taking RH in its all glory and then perturbing the atmosphere to get the result. So this is what stick would produce. You see here nicely cold, active region, then all these hot things around. And this is what deep iris would produce. So very comparable to images, with a huge difference that is immediately obvious, and that is that these things here are much more smooth than these things. These dark coldish features here, they cannot be found, so that's a little bit worrying. These found, but in general, they look quite similar. It's now up to you or the user or the author and so on to really assure and to understand what these things are happening. But here you can see one very interesting property of these machine learning inversions, even when they are done, especially neural network inversions, even when they are done on pixel by pixel basis, is that they tend to produce smoother results than regular inversions. The reason for that is mostly because There is no chi-square as such. We talked a little bit of chi-square, and yeah, I hate to complain. I don't know that whether in Carlos's lectures we paid so much attention to that. I would have calculated some chi-squares by my hand to really ensure how big it is. Chi-square is extremely sensitive metric. The sense that if you have one point that is for some reason outside, that point is going to drag the line toward the pit. And most of these, things here where you see these things very fuzzy are probably not that physically this is grainy like this. Is because your spectra simply exhibit some noise and your code gets stuck into some intermediate solution, or simply in a solution that satisfies the data, but is simply drawn a little bit away from the real solution because of some noisy points and so on. Neural networks somehow, I don't understand why, avoid that. They give you much more smoother solutions than the regular inversions. And they somehow skip over that. Maybe they are just insensitive to this noise or something like that. I don't know. But they seem to work very, very robustly in that way. Okay. And I mean, of course, it's up to you to gauge whether this network does the job for you or not. Probably if you give it a very complicated spectrum and it's not going to give very plausible result. Maybe if you just want to have a vague idea, what's the difference in the temperature structure between active region and the quiet sun, it can get the job done in a couple of seconds for you instead of you waiting for months to get the inversions done. Okay. D is for photosphere. It works much, much better. Here you have a simulated photosphere inverted with the standard inversion code. I don't even know actually which one is which one because I didn't copy paste and they're all the same here. But let's say that this is a neural network inversion. So simulated thing, inverted, then inverted. Why do we take simulated things and then invert them? What's the point of that? The point is that we know the answer. So we can assess how our standard inversion does with respect to the correct. We can assess how neural network inversion does with respect to the correct answer. So here we have a photospheric structure. This is what regular inversion would do. This is the temperature, velocity, magnetic field, neural network, temperature, velocity, magnetic field. And you see the scatters here. They're not huge, and they're really nicely aligned over the line. For magnetic field, it's always hard, right? Because a lot of pixels are very weak. So I should have filtered this or find some other way to plot the magnetic field. Very, very, very good. Very good agreement. However, you should be afraid of things is because the neural network in this case will fail in the same way when a standard inversion fails. What we trained on here, where these results come from, they come from the inversion of neutral iron lines at 1.5 microns. We are so excited about these spectral lines, especially now with the Ionosphere instrument, because they are formed very deep. Well, very deep means 50 kilometers more than visible lines, but still 50 kilometers by 50 kilometers, 100 kilometers. So they're formed deep because the continuum opacity there is small. Line opacity is small, so they probe low regions, and they're very magnetically sensitive. They're in infrared, so Zeeman effect is 3 times more sensitive than for the optical. Plus, they have one of them has huge lambda factor, like 3 or 3.5. So that's a lot of magnetic field sensitivity. You can easily reach like 10 Gauss sensitivity or something like that. But here, as you have seen with SIR and Desire and all the other codes, you will get something for your optical depth at -5, even though you're inverting the lines. Your forward synthesis module needs that. So what you have here is we were looking at the node at the optical depth at -3.4, which is definitely depth that these photospheric lines are not sensitive to. This is how it originally looks in the simulation. So for those of you familiar with Murray simulations, something very commonly seen. This is what standard inversion would tell you. So already from this fuzziness and graininess, you would see that something is not wrong. And here is what neural network would give you. And this actually looks very nice, but it's complete nonsense. What you see here is first what you see here is you see standard inversion simply correlating that node with other nodes because it needs to set some gradient or something like that. So it's a little bit correlated, in this case, with your granulation pattern. And then neural network learns that, polishes that a little bit, and you get this nice looking picture, which is completely nonsensical. Get something like this, you should simply know from the physics, from your everyday knowledge, log tau minus log tau minus 3.4. I don't know it. I shouldn't look at it. I shouldn't pay attention to it. I should just ditch it and pay attention to the quantities that I think I can infer, like the quantities at log tau 0, right? Now I went ahead and did this on some other data, some observed data. This is my favorite slide of all times. This is spectropolarimetric observations from SST, sodium D lines. Here at the top, and I like to use it to illustrate what standard inversion does. These are results of standard inversion applied to sodium data. So here we have continuum intensity. Here we have a D1 line, Stokes V in the wing. So it kind of tells you where magnetic field is, right? What you see, of course, each of these points contains a huge spectrum with huge resolution. This is triple. Triple is a spectrograph, so you get a lot of wavelength points. This is a specific technique, so that is why you see so nice spatial resolution. And you see here that we can infer temperature at, for example, photosphere, but also temperature higher in the atmosphere, right? Then velocity in the photosphere, velocity higher in the atmosphere. Magnetic field in the photosphere, magnetic field somewhere higher in the atmosphere. And the physics behind this we know. It's supposed to look like this, right? Magnetic field is supposed to fan out, become weaker. Velocities are supposed to move from granulation velocities to some oscillation velocities. Granulation is supposed to turn to inverse granulation, and so on and so on. This takes a lot of time, especially with my code, because my code is a little bit slower. It's not so optimized, so it takes a minute or so per pixel. And here you already have hundreds times 100 pixels. It's a lot of time. So what I did, the good thing with my code is that the output are nodes, specific values that you can immediately use for these kind of machine learning researchers. So I took this, applied it to the whole observed data set, and you get a little bigger maps with nice granulation and inverse granulation patterns here. You see a nice plage here, so on and so on, right? The velocity as well from above, so you don't see the pixelization, but this you see it very nicely. You know, all the granules, intergranules, the resolution is very nice. Courtesy of Michiel van Noort, you see that here. Velocities are smaller because there is plage here, so it spends some velocities and so on. And also the same for the magnetic field, right? Nice compact in the photosphere, nice and fuzzy in the atmosphere. But of course, I didn't want to just look at these neural network results. I wanted to verify them. So I compared the standard inversion versus neural network inversion. And for things like that, it works great. Because the histograms of the differences between the temperatures, they're very narrow. The typical width of these differences is 50 Kelvin. Now, some of you might want to say, well, 50 Kelvin is a lot. I want more precise than that. Forget about it. This is just the difference between two metals that are both wrong. So that we definitely don't know the temperature in the photosphere up to 50 Kelvin. We don't know opacities well enough. Our structure here is too simplified. Our forward model is not sophisticated enough, and so on and so on. But at least I assure that I'm making very similar errors in both. Why? How can I tell that? Well, because this, difference between these things is kind of normally distributed, and I can attribute that to some noise. Same for the velocity, some 0.44 kilometers. And I don't know even anymore which velocity is which one, which is neural network, which is this one. What does this tell you? I think I was giving a talk a few weeks ago, and Saida asked me, like, how are these results so good? And my answer was, it's not that network is good, it's that this is simple. There are very few quantities that your line will really unambiguously tell you. And if you really just want to infer them, that is very straightforward and robust. And this is why I said at the beginning, we probably shouldn't like recalculate and recalculate and recalculate radiative transfer equations so often when the things are so similar. For example, in the quiet sun, and not only in the quiet sun, also in umbra and penumbra, the things are similar. We're not interested so much in specific pixels. Okay, sure, sometimes we are because the pixel is very interesting, but most of the time we want to know how much magnetic flux is there, how much is flux preserved here, how much of it reconnects on these scales, what's my power spectrum of my velocity, or things like that. We want statistics on huge number of simple pixels. And that's where neural network can really help you, I think, right? Here is for the magnetic field. I should have filtered it so that all these 0 ones disappear, but you also see that they are very, very, very similar. Right? Very nice data. Yeah. Okay, However, there were people who did much more sophisticated and much more complicated and much more fascinating things, like, for example, Chris Osborne and his collaborators, who developed something called invertible neural network. So I will not pretend to know exactly what are the technicalities of this work. You have to try and read it. What they were trying to do is they were trying to learn the network where both mapping in one direction and in the other direction are optimized simultaneously. And they were so genial, so ingenious, that they realized that there is a way to circumvent the ill-posedness of the inversion problem. What does ill-posedness mean? It means if I give you an atmospheric model and you synthesize, in this case, they were synthesizing, so this output here, so this input was a model atmosphere from Radin. Radin is a radiative hydrodynamic 1D time-dependent code. The outputs, which you can then calculate spectral lines from the model atmosphere. The output were H alpha and calcium 8542 spectral lines. These were simulations of flares, flaring regions. They realized that, okay, from calcium 8542 and H alpha, I cannot unambiguously infer the atmosphere. I already know that. But there is some information that is lost on this process that I can make certain assumptions about and inject it back. They parameterize, they call that also latent space, and they parameterize the parameters living in that latent space and their distributions and so on. And they said, let's assume that these things are distributed in a normal way, Gaussian way or something like that. And when we want to infer back the model atmosphere from this, we're just going to draw some random numbers from fitted, from inferred distributions of this latent space. And we're actually going to get input, but we also can redo that to get the uncertainties in the input. This is what they got. This is how their code performs on Radin data. So it's really reproducing and fitting these spectral lines to a very, very high degree. Also, look at the shapes of these spectral lines here. They're fantastic. They are same. It's because this is flares, right? Simulated flares. Okay, this is on intensity, so it's not spectropolarimetry. Some of these results are not spectropolarimetry, but it's very impressive. And this is what they can infer. They infer atmospheres as they look in simulations. They are on Z scale, not on tau scale. Only thing that the simulation knows, and so on. They apply it to the data. They again get very, very good fits. Okay. Now, by sampling this latent space that we talked about, they can get something like uncertainties in their physical parameters. Really, really well. You can have a look at this paper together. I don't know exactly what it says. Well, what it's doing, but it's their results are really, really, really impressive. And all the concepts that they did there, they were really fantastic. And the thing here, that the big difference with the previous example is that this draws on physics. It draws on physically motivated, physically created atmospheres that contain all the Radin physics in them, and you expect to see something like that back. And this is both advantage, because you know that some things are probably going to be satisfied, but it's also a problem, because what if you're looking for some new physics in your observations, right? Okay, talking about these uncertainties, I don't know if we talked a lot about uncertainties in this school, but we should. And also people in neural networks are thinking about this as well. And some other geniuses, well, very, very clever people also, made this amazing concept of neural networks using so-called normalizing flows. And normalizing flows are type of neural networks that instead of producing results, produce distributions of results. Why do we care about distributions of results? Because when we do inversions, when we do any sort of inference, we don't want result. I mean, we do want result, but we want also to know how certain we are of that, right? I much more prefer you to tell me, well, maybe, today for lunch, there will be 50% hamburger, 25% nothing, and 25% a rock, then tell me, oh, the greatest probability today for lunch is that it will be hamburger, right? Yeah, I want to know all the distributions so that I can make better, decisions about my life and everything else. It's the same here, right? If somebody will really get hung up on some values from the magnetic field, then we'll say, ooh, my magnetic flux is increasing with height. There is injection of the magnetic flux here. But then if that person had reliable uncertainties of the magnetic field, maybe they would recalculate and they would say, okay, within my errors, I actually cannot claim that the magnetic flux is increasing with height or something like that. Okay. It's important to know the uncertainties. This kind of neural network that takes one distribution out, in this case a spectrum, and spits out probability distributions for your parameters is called the normalizing flow. Why is it called the normalizing flow? Because in the process of the neural network, you eventually transform your input distributions into normal distributions, and then normal distributions back to the probability distributions of your parameter. Okay, and then with these normalizing flows, you can get something like this. Did anybody see a plot like this before? Can anybody explain me what kind, in cosmology, you see a lot of these plots. But here is one for the solar physics, and what you have here, I will tell you right now, and you can explain to me what. So I will tell you the things, and you will tell me what we learned from this. So these are S1, S0 parameters of Milne-Eddington model. Eta 0 is the line strength, and this is the line width, and this is the line of sight velocity. So 5 parameters, and there is this 5 times 5 triangle plot. What does it tell us? Somebody tell me. Exactly. So when we infer something from a spectrum, we should always aim to get the probability distribution of the parameters. If I have 5 parameters, that's 5-dimensional probability distribution. Hard to visualize that. So we visualize projections of that distribution. In this case, these are the 1D. We visualize projections. That's what we always joke and we say, this is what you put in your paper, right? These 1-dimensional distributions is what you put in your paper because they give you mean value plus minus uncertainty. But you can also visualize joint distributions, as Nancy said, right? So you have this thing here. This is like a projection of your whole distribution on one plane or on one line, right? So this is where you get these values, and these joint distributions tell you about correlations from things. So when I have a more or less circle like this, it tells me that my line of sight velocity and my typical width are very uncorrelated because it's a circle. But for example, my line strength and my S1 parameter of Milne-Eddington model are very correlated. It's this banana shape, we often call it. They're very correlated. If I change one, the other one changes in predictable way. So on and so on. Very interesting thing to do. And typically, the way for you to produce this plot would be to use something called Markov chain Monte Carlo. Markov chain Monte Carlo are samplers. They basically guess your forward model many times and generate these kind of things. However, normalizing flows naturally produce these things. Why normalizing flows are so powerful. And then what they did is they said, hey, Jaime, calculate bunch of chromospheric lines for us, and let's do that same thing for chromospheric lines. Here, what you can get is you can fit chromospheric lines. You can get not your only atmospheric model, but you can get reliable uncertainties in your atmospheric model. I don't know what are the differences. No, these are different physical parameters. At top, we have the temperature, line of sight velocity, microturbulent velocity. And what you see here is, yes, you see that the temperature is typically very well constrained between 0 and -2. Then later, if you, for example, include calcium 8542, you will get smaller uncertainties. If you don't, you will get larger, and so on and so on. And then they can produce very impressive maps like this. You have photospheric temperatures, chromospheric temperatures, photospheric velocities, chromospheric velocities. Look at this. This is why we do this. We never fit individual spectra. Sometimes we do, sometimes it's interesting. But typically what you will want to do in your research, especially with DKs coming along and telescopes like that, you want maps of physical parameters to put things in context, right? So what you have here is you have velocity at log tau -4, temperature at log tau -4, so it's lower chromosphere already. And then the temperature at log tau -1. Why is -1? Shouldn't look like this at -1. Probably 0. And this is right. And here there are the uncertainties. So they automatically get uncertainties for these parameters, and they can find something that we agree that along this whatever structure this is, I don't know. You get more uncertainties in the velocity and also kind of in the temperature. Very interesting, very, very powerful. Right. Finish talking about neural network and their approaches is that you can also treat things not like individual spectra. You can treat spectroscopic data, spectropolarimetric data like images. How do we treat them like images? Well, we can say, what I look at are the images, which they are, and then different wavelengths are like different colors in the image processing, right? That's what we would do. Different Stokes, also different colors, right? So if I had, for example, an IB scan at 25 wavelength for Stokes parameters, I could say this is an image with 100 channels, right? 4 times 25 wavelengths for Stokes parameters. So Teresa Censio and Carlos Diaz made this neural network, which was actually the first paper of all of these that I mentioned. I think it was the first, where they immediately went for 2D option. Very brave. They input images of Stokes parameters. This is just one of the 2 architectures that they were treated. It goes through this encoder-decoder architecture, and it outputs the 3D model of the solar atmosphere, right? This is our main paradigm in spectropolarimetry that I also don't know if we talked about it a lot. I look at the spectra in X, Y, and lambda. What it tells me is the structure of the solar atmosphere in X, Y, and Z, minus Z. The tau, but okay, that's what we want to learn. We want to probe the 3D structure of the solar atmosphere using high resolution, high spatial and spectral resolution spectropolarimetry, spatial for X and Y, spectral for Z. So Z and lambda are like intimately related to the radiative transfer equation. What they did here is they trained this, of course, because you don't have really, you don't really have a routine 2D inversions which take into account all these, the fact that it's sun, that it's not all individual pixels. So they trained this on simulations and then applied to the real life data, right? And then it has a little bit of advantages for giving you some things that are and a little bit unsettled, right? Because your idea about some parameters that you shouldn't be able to infer from radiative transfer equation. So let's go and have a look a little bit of the results. This is their application to a nice sunspot observed by Hinode. And you can see some very interesting stuff there. You see nice granulation at log tau 0. You see how temperature of the sunspot changes, how you get the inverse granulation around, really nice, and so on. Same for the velocity. Umbra is pretty much at rest, as it should be. The granulation velocities here, they get a little bit more fuzzy, so on and so on. For the magnetic field, deep here, it's more strong, better defined. Keep in mind that the scales are changing. Here it's a bit more fuzzy and weaker. Everything is pretty nice, so on. And keep in mind, they input the image, multiple wavelengths, the 3D structure comes out, right? One go. There's something called Wilson depression. Here is you see how each of the optical depth surfaces, how high it lies on some absolute geometrical scale. So we see here that umbra is a little bit depressed, right? It's a little bit down, penumbra a little bit less, and quiet sun, the granules are generally higher than the intergranules. This is not something that you should be able to learn, that you should be able to infer from the Stokes spectrum. Can anybody convince me why? And the other ones here. Exactly. This is something that is very important for all of us to understand. If I take the whole atmospheric model and I shift it up by 500 kilometers or 1,000 kilometers, I'm not changing it. Radiative transfer goes through it just the same. Everything is just the same. It's impossible for me to detect that thing, right? It would have to move like by millions of kilometers for me to actually see it closer to me, right? That would have to happen. But hundreds of kilometers is nothing. How does this network infer it then? What does it exploit? Where does it pick it up from? Spatial information, exactly, because it knows roughly, okay, when I have the granule here, it's a little bit higher. When I have the intergranule here, it's a little bit lower, and so on and so on. So if I input this in, I will get it back. And now, of course, it's up to us whether to trust this. Because what neural network essentially did here is it learned something from the simulation. It cannot be inferred from the spectrum itself. Technically speaking, this could be completely wrong. This could all be jumbled up or flipped or whatever. But we know that in simulation, we see these things. So what we got as a misproduct here is we got a way to kind of infer these by comparing it with simulations in a way. And since we have no better way to do these things, we might as well accept it, right? Of course, the best way now would be to go and to somehow go and check the physics in this inferred model and see if it makes sense, if all the pressures and motions and so on make sense. But then we are doing the right thing. Now, the nice convenient thing that they found, by the way, here is another unsettling thing, since they don't force hydrostatic equilibrium and things like that, they're also able to find the pressure of the gas at different heights. It's also something that your standard inversion will not tell you. Actually, it will tell you, but that pressure will be directly inferable from the temperature, so it's not the same thing. Another nice thing is that if you, for example, train the network on the synthetic data that has been subject to some instrumental effects, and if your simulated instrumental effects correspond to the real instrumental effects, your network will learn to remove them. It will learn to give you good thing where you started from. So in other terms, because this is Hinode, you will get deconvolution of the data for free. So this is original part of Penumbra. So SIR code would fit it. So this is intensity observed, the intensity fitted. This is how SIR would fit it after deconvolution of the data, spatial deconvolution. This is how neural network would fit it, knowing that the data needs to be convolved with the PSF after, right? Because it knows, it says, what do I have to do so that when the PSF is applied, I get this. And this is what PSF applied to this creates, right? Get deconvolution for free. Why is this only possible for Hinode data and not, for example, for SSD? Because Hinode data, Hinode is in space, right? So it has very well-defined PSF, which does not change, and it's a great instrument, and you should all use it. Okay, good. I think we are done here. And yeah, these are some things that that we can all work on, that we should all work on, I think, which is simply try these things, try to bring some new things, try to verify them, try to convince other people that it works or that it doesn't work, warn other people if it doesn't work. But here are some things that I think we today are kind of worried about and would like to learn. One thing is that we want our neural network to incorporate some amount of radiative transfer. We want the neural network to ensure that inferred model atmosphere and incoming spectrum are consistent in that way. That's hard to do because it takes a lot of time, much more time than any of the network operations that you would usually put in there, but it's doable. It's especially doable now because you have RH, you have SIR, you have Hazel, all incorporated in Python, so you can, in principle, you can add them to your neural networks. Problem is that in the neural network training, the so-called backpropagation requires there are some derivatives there, and these derivatives are response functions. These response functions are still costly. It's kind of open problem, but we would like to have it. Then one thing that bothers us a lot is how to choose the training set. And the biggest problem there is because I can come up with completely different sets of data that produce very similar profiles, and that's a problem. For example, most of your training sets that you will make by hand, for example, by perturbing falsi or something like that, will have something called microturbulent velocity. David already told you, and I agree with him, that we hate it. We shouldn't need it today. Shouldn't need microturbulent velocity or filling factors in the high resolution data. It shouldn't be needed. That's a relic of the past, right? However, with turbulent velocity, without turbulent velocity, I will get some results. It will be kind of, so what do I put in my training set? Do I put microturbulent velocity? Do I not? Then do I take it for simulation? If I do, then I will get kind of simulation-like results back. If not, not sure. So we tried in many iterations to generate various kinds of mock sets. Of course, the ideal thing is you somehow create all the possible atmospheres, even the unphysical ones where the temperature is jumping high in the photosphere and so on. And then you train. But then the more diverse set you have, it's harder to train the network. It's harder to make a network that encompasses all that. So there is some sort of sweet spot there, but it's not like that. We can add more physics and more instrumental effects in the network process itself. What do I mean by that? Well, for example, if you like this idea of getting the Wilson depression from the thing, then use it and add more things. Ask the network to constrain divergence b equals 0. Ask network to conserve something else. Make it so that it fits in there, right? Then another apparently simple, but for me very unsettling thing is, how do I know that my network is optimized? How do I know that it couldn't be simpler? How do I know if it should be more complicated? I don't know. I personally don't know. I don't know if these fancy people from Google know. Maybe they know, maybe they don't. We can maybe ask them sometimes. I don't know. Another thing which is very specific, and what I'm point here is we should. I'm interested personally to see what can autoencoder tell us. Can we compress the spectral data? Can we compress the atmospheres to learn something about their capabilities? Principle, the simplest, the most maybe robust, the most conceptually, strong way to make an inversion would be compress a lot of spectra, see how dimensional, how complex it is. Compress a lot of atmospheres, see how complex, how dimensional they are, and then make a very simple neural network that matches these compressed things, that matches compressed spectra to compressed atmospheres, and then you just compress the spectrum, do this matching, decompress the atmosphere, and you get the both sides inversion, right? That's something that would be nice. And one thing that is by far the most important is write some papers that use neural networks to do something that wouldn't be possible without them. All these papers that you see here are illustrations. They are illustrations how to do something. They're very impressive. They look very good. But go with invert flare, go to Jana and be like, does this make sense? Is this something new? Did I discover something here? And she will tell yes or no, or this is nonsense because of blah. It's the only way to actually accept these methods, and same goes for the inversions. Very often you spend so much time, so much energy inverting something, finding something, and then we write a paper, and the paper is most of the time, this is all the blood and sweat and tears that I spent inverting this data. These are the results. These are the temperatures, magnetic fields, and velocities, and we never learn anything from them. We just present this, and then somebody else is supposed to interpret that. Let's change that. Let's say, okay, I made this result with the neural network inversion, and this is the new thing. I discovered this. I mean, it's hard to. It's easy to say that. It's hard to do that, but that is what I feel is missing. That's it for now. We have 10 minutes left. I suggest you ask questions. If you don't have questions, we can go and in Google Colab and just see, some PyTorch syntax, and I can show you how the neural network conceptually works. Any questions? No. Okay. Okay, good. Then let's find an excuse to do some coding. If somebody is not interested, if they want to go out, you can go and come back at 11. I'm just going to show a very basic thing here. So also I got to test how this interactive medium look like. Okay, so with this. This. Okay, this is a bit small. I'll zoom here. This is maybe even larger. Huh? People in the back tell me if this makes sense. Even larger.
I couldn't access the collab. They gave me the ask for permission. You happen to have
okay,
this?
let me try and change it straight away. There. We don't want viewer. An editor. Editor, copying, or maybe because I changed the name. try this one. This is a very small, very small piece of code. It comes from a bigger guide written by Carlos Diaz. And it is basically just showing you how to generate some data mock set. In this case, the data mock set is generated from a linear function. And our neural network will be the simplest possible dense layer. The simplest possible dense layer will take one input, one output. The matrix multiplication will, in that case, be simple multiplication, right? And the bias will be just one constant. So our network will have two pre-parameters. But since we are fitting the data, which is originally linear, we actually expect to retrieve back the linear parameters that we started from, right? Okay, so this is basically like a linear fit in the neural network formulas. Good. These are some initial inputs for that you need to do. The package that we use for these neural networks is called Torch, PyTorch actually, but the name of the package is Torch, and we are implementing a couple, importing a couple of packages here, and we are initializing some random numbers here because we need them for training, how to start our values, and that's it. Good. So what I'm doing here is I'm creating a set of random data. How do I do that? I set my X in range from -1 to 1. I generate 100 numbers. I create them by some linear function. I'm actually gonna call that K0 is 1.4 and N0 is 0.5. I'm gonna replace this. I'm gonna say it's K0 times X obs minus N0. Okay, this is my linear function. And what does this part here do? Adds noise, right? That just adds some noise so that we have a scatter, and then we're going to plot it as dots here, right? I do that. Works. My computer is now sharing, and it doesn't. I didn't run the previous cell. To plug my computer in for these exercises because it's going to work faster. Okay, we ran this. Ran this. Their data, right? So it's this sounds a little bit like too trivial in the sense I generated the data from a linear function. I'm going to fit it with the neural network that has only one neuron. This is just to introduce you to syntax. If you want, we can later make an input which is multidimensional and learn some output. Like for example, we can make a lot of Gaussians and train a network to learn their positions, areas, and widths or something like that. And we will do that not by fitting Gaussians, but by actually devising a network. Okay, good. So this is where it all happens. Very defined. PyTorch is a bit hard because it asks you to make some things on your own. You just don't just import the layers and put them onto each other. But it has, in my opinion, just the right amount of automation. Like some trivial things are automatized, so you don't have to code them, but you have a lot of control of other things. So what I'm doing here is I'm creating a class called model A, right? It's created from the NN module. It's initialized by providing the dimensions, right? Dimensions are 1 and 1. So this basically, sorry, it's not initialized. This is a only element of our model, of our object here. It's another object that exists, that is in the PyTorch, and then sub package, and it's a linear layer with one input and one output. This is what I did here. Oops, sorry about that. And then this model that I created has one method, has one function. Methods are the functions that are inherent to objects. Like if object is a car, method is open door and something like that. Object-oriented programming, if you haven't seen it before. And I'm going to have what that method forward is doing is it's just acting with the linear operation on the input. We're going to see later how we can stack this. I mean, maybe we won't, but I can show you. And I'm creating a model here just by saying model A, and I run, summary. Summary is supposed to tell me how my model would look like for 1 and 1. And it looks like this. It has 2 parameters and 2 are trainable, and that's it. My input, it only tells me output. So this -1 means as many as I provide, and then output is 1 and 1. 1 and 1 is the only one, but it always has 1 extra dimension because it also has channels or depth. The way I train it is I need to have an optimizer. Oops, sorry. I need to have an optimizer here. The optimizer is a function that slowly changes the parameters of my neural networks that are hidden from us. We never explicitly specified them. We only said we had a linear layer, which is 1 times 1. Okay? And this optimizer has some parameters. I can later explain you what they are. And here, this is a loss function. MSE is mean square error. Mean square error is basically chi-square, right? So in a way, we are really, truly going to fit this data with the linear function. Why is it linear function? It's linear function because I asked it to be, a linear layer. I can ask, and I will try later to add like a activation function to that. So then we will have more trainable parameters. So what we are doing here, this is very good to show you how the training looks like. I will do 100 iterations of training where I will reset my response functions, let's call them that way, my derivatives. I will evaluate my model. I will compare my model with the training data. I will propagate these derivatives backward. I will take the step. What is a step? Step is adjustment of my hidden network parameters. And each 10th loop, I will output what my loss is. Now we can run this. We're going to see how our loss, which is our mean square error, drops through the training, and it gets something. And we're going to print these values. We get 1.38 for the coefficient of for our slope. It was 1.4. And we get minus 0.53 for our intercept, and it was minus 0.5, so it's kind of good. What I can do now is okay, this is just a technicality to change the dimensionality of the data. And what I'm going to do here is I'm going to detach the data, which means turn them into NumPy parameters. And what do we do here is we plot the predicted data. We are predicting from already trained data versus the original data, and you see that we actually did the linear fit. Now, good exercise. I'm not going to go there, but if somebody wants to try it later, we can try to do it together. Good exercise here to actually mimic what neural networks do is you can change this from a linear function to some complicated function, right? Which, for example, you pretend comes from your physics, and then you change the neural network that it's a series of these, for example, linear layers and activation functions. And you see if you can get your neural network to reproduce this complicated function to begin with. But now you at least have some syntax in here and some things in here. We didn't plan any machine learning exercises. I just kept this in case I finish in time. So you can have this somewhere. And if anybody's interested, I can ask Carlos if probably he won't mind if I share the whole notebook with you, that you can see some more involved examples. That's it. Let's go for the coffee break. If you have any questions, approach me and ask them, and I will fire up our first Hazel notebook. We are moving to that after we're done here. You don't have to fire up anything. It's already here. Come again? I didn't link it. You asked me about what this is found from? I didn't link it. If you want to send me an email or a Discord message, and I'll send it. I'll send it to you. Yeah. This and I'll look for some. Yeah. Don't feel obliged to do this now. You can leave this for future now. Get some, some fresh air. I can sit here for the exercise. My alignment. Okay. I actually forgot I have some slides for you before we start. Because we want to see what Hazel actually is and what it's actually doing. So a few slides. I will share them also with you. And but we want to see what Hazel is doing. Okay. So let's leave our notebooks for the moment. We'll get to them as soon as possible. I'm going to tell you a little bit about the code. One thing that we always need to be aware of when we work with these things is that there is theory behind something, and then there is code that does that. And typically, finding the connections between these things is not always so trivial, right? We're showing you how to solve the radiative transfer equation, how Zeeman effect splits, how this, dot, and then you come to use SIR, and then you're like, what is PE in the config file, or what is NG cycles in the RH config file, and things like that. They're different things, simply because our codes rely on a lot of numerical stuff and so on, and we don't know it. One important thing with Hazel is that I was telling you a lot of things that were very abstract over the day yesterday. Abstract in a way that we were talking about one event of scattering in the atom, and now we are in the sun. We are trying, for example, to interpret observations of such a prominence or something like that, and it's not a different story, right? So okay, these are our conclusions from the scattering polarization talk. Important thing that I want you to remember, or actually to remind you of, is that the Hahn effect man itself has a rotation of the plane of polarization and modifies the amount of polarization, and this is expression for the critical Hall effect, which tells you what magnetic fields you're sensitive to. If magnetic field is much stronger than this Hall field, you won't be sensitive to its strength, only to its orientation. If it's much weaker, you won't notice it at all. So let's see what I prepared for this. I don't even remember very well, but okay. Right. So you remember this, right? This was the plot, kinda, for the scalar solution of the radiative transfer equation for a slab that is illuminated for radiation. I talked about this yesterday because Hazel does exactly this. It puts a slab. Slab means something like this above the solar surface, either like this in case of the prominence, or well, it's also like this in the case. Well, actually, it's more like this in the case of the filament, and that slab is illuminated and it scatters the radiation toward you, right? What Hazel thinks, well, what Hazel actually takes or as given, it takes this radiation field as given. Why is it easy for us to assume the radiation field? Because this this angle is relatively large, so it comes from the whole sun. So I can easily take, for example, observed radiation here. Why do I need to take observed? Because it's not only important to know what intensities are coming, it's important to know limb darkening of this radiation. I'm not going to go there, but there is a lot of gymnastics into figuring out how these incoming rays relate to the outgoing rays from the sun and why we need this thing. Right. This was our source function, and this integral here is solved within the Hazel, as well as this thing here. All the free parameters. This is now scalar case because it's easier to remember, but we will have polarized situation in Hazel. All the free parameters that we will be playing here with are given in this equation here. Source function hidden in the code. We don't change it. Tau is a free parameter that we will have, which is typically for these objects from 0.1 to a few, and all the other parameters are hidden in this profile. How many parameters do I need to describe a line absorption profile? Physical parameters. Can anybody tell me? What goes into this? Three, exactly. What three? In the position of the profile, right? The center, which will tell me line of sight velocity. If it's displaced from where I'm expecting it, it tells me something about the velocity. The amount of thermal broadening, which describes my Gaussian component of the absorption profile, which is going to be some kilometers per second, 5, 8, 10, 3. And something called damping. Damping is there because we know that this is not a Gaussian, it's a Voigt profile, so it's described by two different types of broadening. In principle, some of you might think, well, there is also amplitude. No, there is not. This is normalized to 1. Integral of this is normalized to 1 by definition, so we don't have the amplitude. Amplitude is roughly 1 over square root of 5. Okay, so these are 4 parameters here. Right, and this is the story. This is why we have the scattering polarization. This is a reminder from, again, from yesterday. This is how we look at the blob, at the prominence, for example, and that is further modified by Hall effect, right? This is our write-up for the Hall effect. So now we see where are the remaining parameters hidden. Remaining parameters are hidden as some rotation matrix and some, diminishing value here that are basically given by the orientation and the strength of the magnetic field, right? That's what we said yesterday. We said that the orientation of the magnetic field will determine coordinate system, which we will use for the spherical tensors of the radiation field, and the strength of magnetic field is going to be hiding in this, fraction here. What Hazel does is Hazel knows the incoming radiation field in some coordinate system. Then you give it the radiation field, it rotates things appropriately, calculates these things, puts them back in the radiative transfer equation, and solves the emergent profile for you. And then when you want to fit something with it, it does all these things in the opposite order. It adjusts these things until the fit is obtained. As simple as that. There are a few more things that Andreas put in there that are there to make your life easier and to kind of fit maybe some more exotic line profiles. We're going to be talking about that if we have the time. We can. That's, for example, Actually, I can show you right now what it does, and then maybe we can use them if we have the time, right? And Hazel is made. Why Hazel? And Hazel was the original code, which was created in 2008, which was in IDL. Hazel 2 is its reincarnation in Python. It has a lot of nice features. One feature is that it's completely usable from Python in its default form. You don't even have to use any config files or anything. If you want to invert huge chunks of data, you will need a config file. It uses modern data formats, HDF5 in this specific. It uses MPI, which means you can run it on huge cluster, even not on a single memory machine. So you can invert huge maps. If you have a supercomputer, you can invert huge maps in small amount of time, and so on and so on. A lot of these key things are written in Python. So you don't have to dig, inside and, learn all programming language. If you know Python, you can see how these things are parallelized. You can debug them. If something doesn't work, you can take these ideas for your own projects, right? It's open source code. One reason why this is so easy and so seamless is because Hazel was created with few predetermined spectral lines, right? Remember when Carlos told you when you are synthesizing some new spectral line, you need to find all these atomic parameters. I wouldn't say that only 3 people in the world know how to do it, but it does take some digging to sort these things out. So there is some work. Here you don't have to worry about this because the lines are already hard-coded in your code. The reason for that is that physics is so complicated that it's hard to write a generic polarized radiative transfer code with everything there. You can't just spit in a atomic model and get these things. Things are basically hard-coded for helium-1030 and helium-3. Why? Because they both emerge from one helium atom that we were going to look at the Grotian diagram later. So these are the 3 parameters of Hazel: line center optical depth. So it's a little bit different than what previously our profile is tuned to its maximum being 1 instead its integral being 1. Line of sight velocity, broadening velocity, damping, and magnetic field. So it's 1, 2, 3, 4, 5, 6, 7 because it's a vector. 7 free parameters to describe polarized line profile. We'll see that it will work fairly well for most of the profiles we will see, but I will also show you how to use more complicated things. You can, for example, scale your source function, but some additional free parameter. You can use filling factor to combine multiple models, and so on and so on, right? So what code does when you do this, it takes magnetic field, calculates the source term from illumination that you already prescribed. You don't prescribe it, it's hidden in there. Magnetic field, and then it solves radiative transfer solution and gives the scattering polarization and Zeeman polarization, not only scattering polarization, right? So it's a bit more complicated than what I gave you. It actually has the absorption matrix that David told you about, right? Good question that a lot of people would ask now is, Ivan, why are you wasting our time? We'll just take this iron and invert 10A30. It's not going to work like that. Reason why we have this is because 10A30 is a very simple line. You might think that it's a very simple line from this model that I just described, but it's a very complicated line. The reason for that is it's not what I would call atmospheric line, at least not in the most cases that you're interested in. It's not formed within the atmosphere, at least not the one that we consider. It's not like, formed at log tau -5 at 1,500 kilometers and so on and so on. It can be formed at a variety of heights. People even think that it can be formed in corona. The reason for that is because the lower level of this transition is not just populated, through regular processes. It's populated by UV radiation pumping. So you need to have a region where you have a lot of UV radiation to populate this lower level. This lower level is then what we call metastable. Metastable, it means it takes a lot of time to decay to lower states. When it's metastable, it effectively for us behaves as the ground level, in the sense that it stays like that a long time. Then when it's ground level, then there is a possibility that the illuminating radiation field from the photosphere will hit that atom and there will be line scattering there. But before line scattering, there is all this process of ionizing helium recombining, ending up in the lower state of helium 10A30, and then scattering incident 10A30 radiation, which is typically very, very flat because, as Hans showed you yesterday, 10A30 photospheric signature is fairly weak, definitely weaker than the then your signature from your active regions, prominence, filaments, things like that, right? So you cannot use desire, RH, stick, any other code to interpret helium-1030 that you see in prominences, filaments, active regions, and so on. You can do forward modeling for the cases that you're interested in, like for example, what Rebecca and Han did in that paper that we saw yesterday, but you cannot fit these systematic data. It's not going to work, right? These regions, they don't look, I said they're not atmospheric. Why are they not atmospheric? We picture them as some sort of clouds, as some sort of slabs that are completely detached from the atmosphere. All our inversion codes today use hydrostatic equilibrium. Hydrostatic equilibrium, not going to work for this, right? It's not going to work for a blob that suddenly appears. We didn't make an inversion code that works like that yet. Okay, so yeah, for helium-1030, helium-D3, we are sadly limited to using these simple models that don't have all the nice physics that you can, for example, find in RH and desire, simply because it would be too complicated, right? You would have to prescribe this UV radiation, you would have to integrate, you would have to solve many atoms, many nonlinear systems, and so on. You would not simply fit things in time, right? Okay, good. So that's the reason why we have a separate inversion code for 1030 and D3. This is the Grothian diagram. It looks very simple. 1030 is created between these levels here and this level here. So 1030 is actually 3 different spectral lines. Keep in mind that this looks a little bit like this splitting that we saw for Zeeman effect. This is not that splitting, right? It only looks that way. This is one specific level with one specific, orbital quantum number, and then different possibilities in coupling between the angular momenta give you these 3 different J's. And then each of these is split in multiple M's. Okay, and actually lower level is also polarized. How do I know that it's polarized? Well, it has J equals 1. It will split in 3. So my lower level will be polarized. My one component of the upper level will be unpolarized. My one component will be split in 3. This one will be split in 5. So Hanle effect for this is already inexplicable with what we did during yesterday's class. So what Andreas had to do for this is he had to go to a GDO, dig through the book, sit down, derive the code, and so on and so on. This code is amazing, really good, but I think the routines that are hiding in there are still routines that the GDO wrote maybe in 80s and just pass them over because it's hard. There's a lot of quantum mechanics and complicated stuff in there. That's how it works for us. We have to work together. We have to pass on things to one another so that things are to trust each other's calculations, because it would take us a lot of time to develop full polarized radiated transfer code from zero. It also works for D3 line. This is D3 line. Even more complicated. It's actually 9 lines, right? Well, not all transitions are allowed, but yeah, a lot of we can count combinations at some point, but it's forbidden. 3 go and 3 to 1. Fewer forbidden, but there's a lot of components also. D3 is another spectral line that you see in these objects that you could pick. Good. What else do we have? Well, nothing much. I told you about all other these. Interesting thing that you have that I might show you tomorrow if we get the time is that Andres integrated SIR code into this, which means he recompiled the SIR code in Python. You can call SIR code in Python, again, for some hard-coded spectral lines. And these are most of the spectral lines that are found around 10830 and D3, for example, silicon 10827. So you can simultaneously model them or invert them. Why is it important? Not because there is physics that is valid for both. As I said, silicon line is formed in the atmosphere, helium outside of the atmosphere. But sometimes in the spectrum, they will overlap. So it's convenient to model and fit them together in order to avoid some systematics that can be created by this. All right. Good. We're done. This was a little introduction to just remind you what we talked about yesterday and what we are going to do now. Now we're going to fire up the code and we're going to see what happens. Typically, what I'm going to do here is I'm going to walk you through the cells. Then we make a little break, 5 minutes. You can change things and see if it works. I walk there, see if things are there. Take it easy. Okay. This is our notebook. What I opened. Okay, let me first close all these other things. On here, so this first cell just imports our needed packages. Should I zoom further, or it's good? Oh, the notebook is, yeah, you clone my Git that is Becca linked on the page, so you can find me like this. Repositories, you go SP 2022. Principally, you should download all these things because some of these files are important for Hazel to work. The proper way to do this is you go to some folder on your computer. A Git, you activate Hazel probably. Environment that you made, and you say Git clone and then the web page. You clone it into a folder called SP 2022. And you can enter SP 2022, things are going to be there. And then, for example, let's say I made some mistakes, I want to correct these things during our exercise today, I'm going to update these things. You just do git pull, and it's going to download any updates if there are. Okay, but we don't have to worry about that now. Go ahead. Resend the link. Just this. Good. So when we are there, okay, let me then turn everything off. I'm not gonna use that one. I'm gonna delete actually that one. Oh. So I have it in my own way in the codes folder, and when you do ls here, you're gonna see a bunch of files, and the one that we want Hazel 2 forward. I didn't show you any examples yesterday because I reckoned it's much better to see examples of the polarized profiles by calculating them yourselves. So what we're going to do now is we're going to type Jupyter notebook Hazel 2 forward. We're going to run it and see what happens there. I already made a mistake. What mistake did I do? I didn't activate Hazel environment, so this will not work. So if your notebook loads, run it, and it says no module named Hazel, that is because of not activating the environment. So every instance of the kernel of terminal needs an environment. On the activate, 2, change here at the beginning, 2, and now when we do it, this first command here broadened my my cells so that they fill the whole page. Yeah. Oh, and we can also do this. I'm importing Hazel for Hazel functionality, NumPy so that I can meddle with the folders, and then matplotlib to plot stuff. Okay, and I'm going to specify here some things about the matplotlib so I have larger fonts in my plots. Nothing special. Important thing to make peace with before we start is to understand this picture. Picture here is taken directly from Hazel paper, 2008. Hazel stands for Hanle and Zeeman light, right? And there is a lot of angles here that are telling us the orientation of our coordinate system with respect to the thing. There is a big difference here between the things in our natural instinct to position things in our own position, right? When we talk about models, about solar atmosphere, about these things, it's natural for us to position ourselves on the solar surface. So this is the point the light is emerging from, right? And these are X, Y, and Z in the local coordinate system. And Hazel will assume that Z goes along the heliocentric normal, of course, right? So this is Z. This is the axis of symmetry of radiation field. It's important. And X and Y can be oriented any way you like. They actually don't really have a meaning here. They're not important for radiative transfer here. They're important for the magnetic field, though, right? This is the orientation of the magnetic field. It's given by two angles, theta B and chi B, what I typically call phi B, right? So magnetic field is important for it to be oriented. Typically, we're going to say that X is oriented, scratch that. I will tell you now what we'll assume. The other important direction is the line of sight, right? Where we are looking from. Determined by two angles, theta, and this theta is typically our heliocentric angle, which basically tells us where we are on the disk. Not clear to you, ask immediately, and let's clarify that. But if theta is 90 degrees, it means we are looking at the limb. If theta is 0, we are looking at the disk center, right? If theta is 0, it means I'm looking down Z-axis, I'm the disk center. If theta is 90 degrees, I'm looking along X, I'm on the limb. Remember this, it will be very important in order for us to understand different regimes of Hanle effect and remind what happened yesterday. Remember what happened yesterday by looking along X. Why do I say along X and not along some other direction? Because we will always assume chi equals to 0. Doesn't make sense to allow the chi to vary, because what actually matters is not chi and chi B, it's the difference between them. It's always advantageous for us to assume that we are along chi equal to 0. And finally, there are these A1, E1, and E2 that we spent a lot of pain yesterday about, that determine the orientation of the radiation field, that determine our direction for expressing polarization. You are now like, okay, man, we know that gamma is 0. It doesn't have to be 0. It depends on how your observers define that. Get the data. If you don't know what gamma is, it's 99% of the time it's useless. Don't know how they're measured, in which coordinate system are their quantities expressed. On the disk in Zeeman profile, it doesn't maybe matter that much because it's just the rotation of the azimuth. But for scattering polarization, it's essentially important. Because if I'm thinking that it's 0 and I'm expecting negative polarization on the limb and I see positive, I will think that there is magnetic field. But if the person who observed defined it as positive already, maybe there is no magnetic field. See what I mean? It's really, really important to know what gamma is. It's a great pain to make sure that you are at the same wavelength as the observers. Okay, so we'll go back. I have this copy pasted on few places during the notebook, so we will go back to this. But this is how you run most of our exercises today. Depending on how fast we go, we'll go on the synthesis of models, and then a little bit later on the inversion of synthetic models. Tomorrow we will fit some individual profiles, or if we go really fast, we might fit some maps or some extracts from maps. Okay. So if we first initialize the Hazel model by saying Hazel.model working mode synthesis, okay? So creates this object here called mod, and then we can fetch and do various things with it and fetch things with it. And we specify here some parameters of the model. We first specify a spectral region going to be put in call this in entry, let's say, of the dictionary that is called spec. Okay, so what I'm asking for here is I'm asking current grid from 10A25 to 10A31, 301 steps, which means my step is going to be what? 0.01 angstrom, right? Then I have some keyword called topology. What does topology do? Topology is telling me what am I synthesizing. The simplest possible topology is chromosphere. Chromosphere means chromospheric slab, right? This means I have one slab. I could have two slabs. I have one slab like this, one slab like this, or one slab like this, one slab like this, and then they have some filling factors. Or I could have a photosphere in the chromosphere. These are all fancy features. We will go to these fancy features if we have time. If you don't have time, you go to Hazel help page and you see how Andreas uses them and you can play with them. Doable, I promise you. And here we specify our first important thing, line of sight. Line of sight are angles theta, chi, and gamma in order of appearance. So let me write the command there. Write the comment there so that we know. Loss is theta, chi, phi, and gamma in that order. Okay, so we agreed that azimuth is 0. We're always going to keep it 0. Gamma is 0, which means that if our linear polarization is parallel to the limb, it's going to be negative. It doesn't matter yet. Why does it not matter? Because theta is 0. What does theta 0 imply? Where are we looking? Disk center. Very good. Then I'm going to create a chromosphere in my code. I'm going to specify it as this topology here that we just made. Spectral region is going to be this spectral region here that we made. Height, well, we forgot about this. I spoke yesterday a little bit, and I asked you to discuss what happens when the height of the slab changes. As the height of the slab changes, the angular distribution of the incoming intensity changes, the amount and the anisotropy of the radiation both change. So height is important for us. The reason why height is not a free parameter in Hazel code is because it's very degenerate with some other things. So we hope we can infer it somehow else. For filaments, we play a little bit with the value. For prominences, we know what the height of our pixel is because we are off the limb. You can just say that this big is 7 arc seconds. We put 7 arc seconds. Here I put 3. 3 is very little. How much kilometers is 3 seconds? 2000. Which spectral line forms around 2000? Well, I don't know, but something very high, right? Right. Where does Lyman alpha form? Almost 2000, right? Yeah. So it's almost in the model atmosphere. This would almost be in your file C, but we can also put much more, right? Now you might be confused. Why is he putting this here? This command, the line 10830, tells you only take into account 10830, right? Because in principle, the code could allow you to fit simultaneously 10830 and D3, so you don't do anything else. And this next chapter here tells you in which wavelengths to take into, in which wavelength ranges to take into account 10830. Go ahead. You see the projection. Well, sure, if it's not really on the lip, but a little bit behind. No, yeah, sadly, no, not here. Yeah. Yes. Yeah. Yeah, you're right. Okay, and this here went out of text, so I'm going to do this. And this command mode setup is going to prepare your code for synthesis, and that's it. So we only specified everything else by the model, but the model parameters, right? So here I'm going to list the model parameters that we have. Once again, these are they in order of appearance: px, by, bz. So that chose by default not to work in theta, phi, and that, which kind of makes sense if you think about how we would generally express them. We would prefer bx, by, bz maybe. And then there is optical depth. 1 in this case. Line of sight velocity is 0, so our line will not be moved. Thermal velocity is 8, and damping is 0.1. Should I zoom more? This is how I pass my model the parameters. There are 2 parameters which I didn't list here. There is a mysterious one here and a mysterious one here. Okay. The second one is the filling factor. I don't have to use it unless I combine multiple slabs. This one here is an artificial factor called beta, which tunes your source function. Why would you want to do that? Well, for example, if you have a flare, on top of the scattering, you will have some thermal emission, which is not explicable by this model. So I have to artificially tune my source function. We will see later that by introducing this beta, we can create emission lines. We want. which you generally won't see on the disk in 1080. Then I'm going to do mod synthesize. This creates my spectrum. And then my spectrum is hidden here, hidden in mod.spectrum. Then spec1 is specified here. Then dot Stokes. There are other things in addition to Stokes. We're going to inspect them later. But for the moment, I'm going to run all this. Happened. And I always like to do, whenever I get a quantity, I like to do shape. Why do I like to do shape in Python? Because it tells me what I'm looking at. Does it make sense? What I'm getting is I'm getting an array with 4 times 301 components. Okay, that makes sense because 4 is 4 Stokes parameters, 301 is 300 wavelengths. Then we go down there and plot them. Just a very easy way to plot them. If you prefer doing like big axis or something like more object involved, it's fine. I just like good old plot. I run that cell, I get the profile. Absorption profile, Stokes I, 0Q, 0U, 0V. Let's discuss. Did we expect this? Yes. We expected V equals 0 and U equals 0 because there is no magnetic field. Why did we expect Q equals 0? You're looking at this center, exactly. We look at this center, everything is, isotropic from all the sides, there is no polarization. Why is the spectral line absorption line? Not polarimetry, but important to keep in mind. There is source function in the slab. Source function emits. Why is then line absorption line? Correct a bit. I didn't explain you one keyword. Pick up, Yingji. You have illumination from the lower atmosphere. It creates some source function. But what is a boundary condition here for us here? I skipped over that. It's given here. Our boundary condition is 1, 0, 0, 0. 1 means I have continuum radiation and intensity, and the rest of my boundary condition is 0, 0, 0. Okay. So why is this absorption line? Well, we didn't go over that, but it's a very interesting effect. So slab is illuminated by this field, but because it's not illuminated from all sides, but just from a cone, the value of the source function is lower than the incoming intensity. So when I integrate, even though it's emitting something, it's not emitting enough to compensate for the incoming intensity. So this seems to us like an absorption line. Okay. On the limb, though, because boundary condition is going to be 0, we're going to have an emission line. Okay. So we understand this plot. It's fine. Let's start changing things. Next cell. So there is no polarization. Why? Because we're at this center. Let's move off limb. Let's move a little bit away. I'm not moving full the time to the limb. I'm just changing my theta to 60, keeping everything else the same. And this is a little bit streamlined because I'm putting everything in the same cell. I'm a little bit paranoid, so I always delete the model after calculating something. You don't have to do that. You can maybe just reinitialize parameters. Okay. I do that. 2 changes, right? I'm telling you now some also technical stuff related to Hazel. Intensity changed a little bit, still absorption line, but continuum dropped down. And there is now some linear polarization. Why is there linear polarization? Because we changed theta. Okay, that's expected. Why did continuum drop here? Limb darkening, exactly. So as Brian said, of course, you cannot expect this in advance, but what Hazel will do, even though you gave it 0, 1, 1, 1 as a boundary condition, it will automatically limb darken this radiation if you are off disk, right? Okay. Good. This is what you get. Okay. Good. So now we can change inclination angle. I will leave you later to write maybe a loop or something to show how this, changes with inclination angle. But we see here how weak the polarization is. 0.5%. I can go a little bit more to like 80 here. Goes a little bit deeper, right? It should scale with, in the simple Zeeman triplet case, it should scale with sine squared theta, right? Remember that from yesterday. Here it's impossible to tell because this is not normal Zeeman triplet. It's combination of multiple lines, so we don't know. But it's going in a good direction, right? I'm going more toward the limb, I get more linear polarization. Now we're gonna mimic a case that we played with yesterday, which was something off limb, and we're gonna do all our Hall effect calculations on that one. So here, what do I need to change in order to make this into off limb? There are two things that I need to change. Theta and the boundary condition, right? So when I'm off limb, my boundary condition is 0. Keep in mind what this boundary condition means. It's not the boundary condition for the anisotropic illumination radiation field. That is hard-coded in the code. This is boundary condition just for your line of sight, okay? Just for that. So I'm changing that. I'm putting 90 as theta here, and in boundary condition, I'm putting 0. I'm gonna run that. Oh, my linear polarization went all the way down. Good. Okay, I'm going to change the range for Stokes Q. Where is it? It's here. Say 3 to 3. And you see, in this case, the linear polarization is around 3%, and it's negative, which means that we are in concordance with the formalism used in the code, and it's negative. Why? Because it's negative because of this number here. Right? We change this number to 90, it's going to become positive. And this is the number which comes from your observers. Come. Nice. This is good. The line is in emission. Why is it in emission? Because now we only see the source function of this. Another technicality for you to remember, Hazel will automatically normalize off-limb things to the maximum of the Stokes height, right? So now, if I change some parameter, this is always going to be 1. Okay. Let's investigate this thing about the height. So we said that height should change the polarization, that further away something is, the more polarized it is. Well, good, let's test that. I'm changing that a little bit here. I'm going to create 2 models here. Okay, I don't know why this tau is here. I'm going to create 2 models, model 1 and well, they're both called mod. I don't have to create 2 models because I'm always going to copy my contents to this Stokes 1 for array here. So Stokes 1 is for the old slab. I didn't have to redo it, but doesn't matter. For the second one, I'm going to have height of 30 arc seconds. 30 arc seconds is a lot. It's a prominence that is maybe even, exploding or erupting or something like that. And I'm going to compare the profiles. And this time I'm doing it on the disk on purpose, okay? Because I want you to tell me something. There are 2 differences here. Sorry. It sometimes skips, so I don't know. We are doing it first off the limb. Off the limb, what do we see? Let me also add some legend to these codes here. So label arc seconds. Go page 30 arcs. Do little PLT legend. So off limb, 2 different heights. Profiles look the same because they're normalized to 1, right? U0, V0, we're all happy with that. Linear polarization, much stronger when we are 30 seconds away. Why is it so? Because the cone decreases, the anisotropy is higher, my J02 is larger, my polarization is stronger. I mean, it's larger compared to J00. It's actually, they both decrease just at different rates, right? Because I'm integrating over smaller end. Now let's do that on disk. so that I can ask you an additional question. So this is on disk setup. I don't know why I put this tau here again. I changed line of sight to 70 degrees. So it's on disk, but still on the disk center. Boundary is 1, 2 different heights. 2 different heights. I get this situation. I need to shrink this a little bit here. Lower can go. Nice. Okay, and let's, we don't need legend, it's the same as before. Actually, let's add legend to be pedantic, because maybe later you will review this. Seconds here. And PLP legend. Okay, like this. This is 2 different heights of the slab on disk. On disk, normalization is always with respect to the continuum. So we have higher polarization when the slab is higher, makes sense. We also have a little bit deeper line. Can anybody explain me why that is so? Not related to the motion. It has to be related to the height, because everything else is the same. Why is it related to the height? Go ahead, Jonathan.
Error, so it's being less illuminated to the source.
Exactly. The slab is higher, the cone is narrower. When we integrate it, source function is lower, and it less contributes, so our absorption line is deeper, right? Absorption line. This is a great way to always think about absorption lines. They're not absorption lines. They're the lines that are bad at emitting, right? They cannot compensate so that we have flat continuum. If you had pure black body, no matter how many line processes you have, you would not see spectral lines. Try it. Take SIR, make flat temperature structure, put as strong spectral line as you won't see it. Because it's the same source function for everything. Good. Okay, this also makes sense. We clarify these two. That line is a bit deeper, polarization is stronger, and it's good. So now we need to add magnetic field. For that, we're going to go back to this sketch here, right? I'm going to put us on the, let me see, I'm going to put us on the limb first. So at the limb, we're looking along X. How do I know we're looking at the X? Because chi is 0, right? That's what we prescribed. So we're going to start by first adding magnetic field along Z, magnetic field along X, magnetic field along Y. We're going to discuss these 3 cases. We're going to go to lunch, and then we're going to do more complicated stuff after lunch. Okay. Here I am at the limb 90, 0, 0, 0, 0, 0 boundary condition. Magnetic field is 0, 0, 1, 0, 0, 100. So I have 100 Gauss along Z. And what I'm going to do is I'm going to show it here. Sorry, that is needed at all. This was the referent model with no magnetic field. Okay, good. I'm going to copy its contents to Stokes 0 here. Stokes 0 is going to be our spectrum with no magnetic field. And down here, I'm going to create everything the same except with 100 magnetic field along Z, and I'm going to compare my new Stokes with Stokes 0. Run this, run this. I get that they're almost completely the same. 100 Gauss, wrong magnetic field, yet they are completely the same. Can anybody tell me why is this so? Bravo. Magnetic field is along Z. Radiation field is already symmetric with respect to Z. So magnetic field cannot rotate anything, and it cannot do anything. It's already, so we said yesterday, when magnetic field is aligned toward this, J02 lies along the magnetic field, Q is going to be 0, this Q multipolar component, the Hahn effect does not act there, right? What was the classical explanation? When there is magnetic field along the oscillate, the direction of circular act. If magnetic field is along the axis, that is also the axis of the rotation of my dipole. What magnetic field will do? It will exert Lorentz force that is either like this or like this, which doesn't change the orientation of my rotation plate. It just stretches it a little bit, it shrinks it a little bit. So this little difference that you actually have here is probably Zeeman effect. Probably little influences of the transversal Zeeman effect that make our Qs not exactly the same. So what? I forgot to ask you something. I forgot to tell you something. Back to these, not to these. Quick. This is criterion for critical Hanle effect, right? Lambda factors for atomic lines are typically order of few, 1, 1.5, 2, and so on. So let's assume it's 1 for helium line, because it's also hard, because it's different components, so different lambda factors. What are typical values of these Einstein coefficients for solar lines? Do you know? Told you about strontium yesterday. Go ahead, Dushan. I know you know. 10 to the 6 to 10 to the 8. For helium 2030 line, it's exactly 10 to the 7. Okay. Exactly 10 to the 7, our critical Hanle field is roughly 1 Gauss. They're most sensitive to the order of the magnetic fields of the order of 1 Gauss. Strontium 4607, it's 2 times 10 to the 8. So you might want to be tempted to say that critical Hanle field is 20 Gauss. However, it's even higher because their magnetic field has to compete with so-called depolarizing collisions, which make your line even less sensitive to the magnetic field. Okay, still 20 Gauss is small magnetic field. Even 100 Gauss is small. Okay, this is 1 Gauss. Okay, good. I just wanted to clarify this because, yeah, we should already see influence of the magnetic field when we put it to 1 Gauss. Good. Okay, now let's change Bx. Bx is magnetic field along the line of sight. Let's be wild and put it to 1 Gauss. Okay, I'm doing the same. I'm recalculating the model, saving Stokes, comparing it with the original one that I'm never changing. I do that. Whoa. Bx, I will do this. Better. Hate when this happens. Yeah. This is the cell that we're changing now. Run it. There we go. My line of sight. I have my line of sight magnetic field of 1 Gauss. My Q has almost completely been turned into U. Why is this so? Do you remember what was happening? Magnetic field acts along the line of sight. There is precession, and one part of my Stokes Q turns into Stokes U because it's a decaying, this damped oscillator, damped rotator in this. Can anybody guess what would happen if I put magnetic field 100 Gauss? Saturated Hanle effect. You remember what happened then? Nothing, because we had this Rosetta pattern completely, isotropic, equal in all the directions. Let's see if that happens. It does. But I suddenly have Stokes V. Why is Stokes V here? Zeeman effect, right? So there is no, hey, stop this, start doing this. There is everything acting all together, as I said. Scattering polarization Hanle effect creates polarized emission. That polarized emission then propagates according to the, absorption matrix, which is determined by Zeeman effect. Good. Right. So typically, we put here even smaller magnetic field. I think lambda factor here is larger than 1, so it's even sensitive to smaller field. Let's put half a Gauss. Already half a Gauss is strong, right? To 1 Gauss. You can still see the change. 0.02 Gauss. That is now a little bit less. Already 0.01 Gauss changes are in principle noticeable by the helium-10 line. Of course, in practice, never see this such a weak field. Now what I want to do is I want to do the same thing with BY. Okay. Convince you of something. I'm again going to change it to like 1 Gauss. Everything else is the same. BY equals BY to make this calculated. And this is what you see here. There is no Stokes U. It's only the diminishing of Stokes U. Because now I have a different axis of the magnetic field. My it's hard to explain this, but my precession looks different, and I don't get any Stokes U there. I just get the diminished Stokes U. We can increase it to larger. Important thing: magnetic field perpendicular to the line of sight and perpendicular to the axis of the radiation field never completely destroys linear polarization. It diminishes it up to some point. This is why the so-called turbulent Hanley effect that we will talk about today works. No matter how strong magnetic field is, it never completely destroys the polarization. But we're going to stop here. Oops. We're going to stop here. We're going to go to disk center case after lunch. We're going to look what happens to the disk center, and we're also going to turn on some more strong Zeeman effect. Yeah. And then I'm also gonna, we're also maybe going to see Paschen-Bach effect and things like that. Good. See you at 1:25 sharp.
Before we start, I want to do 2 quick polls. I know half of people are missing, but it doesn't matter. One question, show of hands. Has anybody tried to install the disambiguation code for tomorrow? You tried, and I think you didn't succeed, and you tried. Did you succeed? Okay, so we have one person with the disambiguation code installed. Okay, I would encourage you to try if you guys get a chance, because I think Graham is he didn't expect everybody to have it. But how he was going to go through the lecture involved some Jupyter notebooks and reading out the disambiguated data. Second thing, he gave me a new tar file for the disambiguation code, so I need to upload that and then let you know when you can download it again. Because he's changed something in the Fortran to make the output more easily readable from Python or something along those lines. And my other question, I cannot remember. So we're going to leave it at that. I'll let you know probably within the next hour. I'll upload the next tar file for the disambiguation code, and please do try to install it sometime today before tomorrow's lecture at 8:30.
We're going to take it easy though, and the afternoon is going to be very relaxed. We're going to do 55 minutes now, then a little break, then 55 minutes again, then we're going to squeeze Q&A session at some point and so on. So it's going to be very flexible. I want us to go through this and the next notebook, and then maybe if we do well on time, we can make a little break for me to show you some more advanced features. And I'm trying to leave working with the real data for tomorrow, but we might actually look at some real spectra, right? Okay, good. So this is where we stopped, right? We convinced ourselves of 3 things. One thing was that magnetic scattering polarization is completely immune to the magnetic field, which is situated along Z. Of course, in this viewing geometry where we are looking along X, and object is on the limb. All right. then we saw that in X, magnetic field is very quickly destroyed by the the scattering polarization is very quickly restored by the magnetic field. I think already 10 Gauss is almost completely gonna, well, yeah, already 10 Gauss almost completely destroys this. And then for Y, we said that even strong fields which are perpendicular both to your axis of, heliocentric normal as well as to your line of sight, that they don't completely destroy the scattering polarization, right? So now what Hazel can do is that Hazel can, yeah, okay, good. Hazel we will eventually see how it fits the observed profiles in order to infer this magnetic field vector. Something that you're already feeling and that we mentioned yesterday is that in principle for the typical magnetic fields that you find in some solar structures in the chromosphere, filaments, prominences, these magnetic fields are already saturated, right? Magnetic fields that we expect in prominences and filaments is tens of Gauss, few Gauss to tens of Gauss, as we see that already 1 Gauss is saturating the magnetic field here. So we will not be able to always infer strength of the magnetic field, but we will typically be able to infer the orientation of the magnetic field. Right, okay, good. So now I want us to just convince ourselves that Zeeman effect is also going to play a role, and it actually does play a role because you also get helium-1030 in sunspots. So sunspot chromosphere can be probed by helium-1030, which is interesting. If you are into that kind of research, you can complement your photospheric and chromospheric observations with, helium-1030 observations, and their Zeeman effect is dominating. And we actually have a sunspot. The FITS file that you have in the data folder that we linked is a sunspot where Zeeman effect is responsible for the polarization, and you will see that we can infer the magnetic field. Okay, good. So what I have here now is another model. Okay, I need to, it's another model that is now at the disk center. So tau is equal 0. Boundary condition is 1. Okay, good. This is all as it was. There is one big difference. The one big difference is that here in this set parameters thing, I additionally decreased my source function in the slab. Why did I do that? This is not physical. I'm trying to achieve something. Does anybody have an idea? So this is a parameter that I said I will not touch, right? But here I artificially put it to less than 1, which means that it will shrink my source function. Okay? So can you folks tell me why did I do that? I just noticed it on the break, but I remember very well why I did that. So does anybody have an idea why? No, not necessary. I mean, yeah, okay, you could say that. Okay, we're gonna play a little game. I'm gonna put it to 1. Okay. Calculate, take a look. Spectrum. Okay. Try to remember as many details as you can. Whoop. Here. What changes? Now even more cheating. Whoop. Whoop. What changes? Well, the source function determines how deep my line will be, right? You agree with that? But the trick here with Hazel is that the source function, if I put it to 1, if I put this parameter here to 1, source function is determined by the height of my slab, and therefore it will, no matter how strong I make the line, it's always going to saturate here. By the way, I want to point something here. I think you already know this, but optical depth, we always think about the optical depth as kind of optical thickness in this case. We always think about it, it's a parameter that determines how strong your line will be. Not quite. I can make optical thickness equal to 50. And my line is going to saturate here. The line can never drop below the source function. The line cannot be deeper or in case of depth-dependent quantities, the line cannot be deeper than the smallest value of the source function. That's why non-LTE lines are so strong, because source function there drops to very small things. and I want deep line because I want to have large V, because V is proportional to the derivative of I. So what I did here to further increase V by a little bit, I decreased this. I set tau to, for example, 2. And now we have nice, strong V, right? We don't have to do that. This was just I was just playing around with it. We can put it back to 1 if it's bugging. Okay, good. So now we are at the disk center. BZ is our line of sight component. BX and BY are our plane of the sky components, as we like to call them, right? And these are the linear, these are the polarization signals. So we have strong Stokes V. This is not really strong. This is strong for helium-1030. In general, this is 5%. It's not a big deal. You saw very easily that iron lines reach 20% fairly easily, right? And linear signals are around 0.5%. Okay, and what you see here is, I think, Paschen-Bach effect already. So this line is very sensitive. Very quickly go to Paschen-Bach effect regime. How do I see it? I see it because these profiles are not symmetric. They're very asymmetric, right? And that's because when we have Paschen-Bach effect, energy levels are distorted in such a way to kind of create these asymmetric profiles, right? Good. What about weak fields? Okay. What I'm going to do now is I'm at the disk center again. Okay. At the disk center, pay attention. Boundary condition is 1. I have a magnetic field that is oriented along Z. You're going to see what happens there. Put this back to 1, not to confuse you any further. And voila, there is Stokes I, Stokes Q, even though I'm at the disk center, and then Stokes U and Stokes V are 0. Why do I have Stokes Q here? Anybody remember? I'm at the disk center, yet I have Stokes Q. What's the magic? Very good. Magnetic field is in X direction, and it's not longer Z that is my primary axis for determining the scattering polarization. So I need to rotate all these, spherical tensors for the radiation field and make them make the polarization, which will change the values simply and create some polarization. Of course, it's not only rotation, it's the influence. So if I made this magnetic field very, very weak, I would get 0 Q, U, and V, right? What we talked about yesterday. Very good. So we can play with that. We can put, for example, both X and Y. In case we get rotation, we get linear polarization in U, right? And we see that this is a little bit like Zeeman, right? A little bit like Zeeman. In the case that now I did 45 degrees magnetic field in plane of the sky, it turned everything into U. So already from the ratio between Q and U, in this specific case, I can learn something about my azimuth. Let's see if BZ changes something. Well, it diminishes the polarization a little bit, right? But it's still there, creates some very weak V. Okay. Very good. So yeah, we will see maybe through some examples that actually one of the main parts of all these inversions here, of 1030 inversions in general, the limiting factor is very often getting reliable estimate of your line of sight magnetic field from Stokes V. Because that allows you to overcome this, because if you know orientation of your magnetic field and you know at least one component well, and that one component that you can learn well is from Stokes V, then you can know your full vector, right? You just scale it. I'm going to convince you later that sensitivity is really poor, actually, that it's confined to a certain range of magnetic fields. Okay, good. So now we have this. Good. Okay, so now I'm going to actually let you explore things a little bit, and pick up your own geometry, whatever you want. You can share the screen later, the same like you did with Carlos to show, and make one plot that doesn't only illustrate one case, but varies some parameter. It can be optical depth, it can be velocity. The most interesting is if it's magnetic field, and so on and so on. Okay, I'm gonna give you some minutes to try and make that on your own. So, and then we can play with that together. Right? Let's say we get let me just see a show of hands. Does this until now work for everybody? You could run all the cells. Okay, so then you just need to make a few for loops and it's going to be fine. Right, for that, I think we need to loop in a little bit different way. Make your own, I will make my own. I never got used to this. Those of you who really use Python, you're maybe used to this, but for me, using these objects, like always. I will choose, for example, to vary line of sight magnetic field on the limb. See how really sensitive my line is. You guys can choose something else. The only thing that I need to do is to change BX 6. This, and I'm going to say if S1, see if this works. The height is a bit high. I'm going to decrease it. 5. This is, so I was paranoid before without any reason. You can just change the model parameters and resynthesize and you get new one, right? You don't have to delete and create everything ahead, okay? This works. V is not defined. Because it's called V loss. Okay. Okay. I is not defined yet, because I'm bad. S. Okay. Here we have something, but it's a mess because the plot is very small. Hmm. This legend to be smaller. Try font size. Good. So I did something here. Maybe not the. Yeah, no, it's fine. But on this, after the I see. Voila. Okay, how many people made it this far? Coded this on their own. 1, 2, 2, 3. Okay, good. Thank you. Okay, what am I doing here? I'm choosing some configuration, right? You can make it any way you want. Some inclination, some whatever. Just don't change the azimuth. I mean, you can also change azimuth to see what happens. You can also change meaning of the angle theta, of the angle gamma, and so on. Here, give some parameters. Optical depth. I'm using optical depth. If you are on the limb, it doesn't really matter because the code is going to normalize everything with respect to your line center. If you're on the disk, everything much smaller than 1 will be barely noticeable, right? This is your velocity. Typical velocities that we encounter in photospheres and chromospheres are a few kilometers per second. You can estimate meaningful, value for this by substituting the mass of helium, taking temperature of several thousand kelvins, and finding the appropriate thermal velocity. In principle, there is more than just thermal velocity. So typical values defined in prominences and filaments are like from 5 to 10. We're going to see later when we extract the data. Then magnetic field, here I chose to change it, right? Does this result make sense? Let's see what happens here. So Bx is this, in this specific case, line of sight magnetic field. What I got here is that for the magnetic field of, first of all Stokes I are the same for all the magnetic fields. Why? Well, because the only way for magnetic field to influence Stokes I is either through some coupling, through scattering polarization, but for that my polarization would have to be very strong, or through splitting, through Zeeman effect. None of these things is here, okay? What we see here is we see linear Stokes Q going from some 3%, going very quickly down toward the 1%. It would go even lower if I pumped up the magnetic field, right? And the separation between these is smaller and smaller, which means I'm already in this regime of magnetic fields less and less sensitive to the magnetic field. Stokes U also starting from something, right? And then it's getting higher. Then it's going to start decreasing. We can try and get that. What I'm going to do is I can maybe increase this and say 0.2. Right? First got increase, and then I got decrease. I think at least. Let's see. Here we got very quickly the shrink. Get even stronger step. Take 1 Gauss. There we go. There is hop, hop, hop. There's some blue. Shrinks very quickly. Here also. Very quickly. So back to our standard Bx. Here. What we get is we get Stokes V because this is our line of sight magnetic field. But look how weak this Stokes V is. 10 to the minus 4, right? 10 to the minus 4 is barely measurable today, even with spatially unresolved observations. We will see tomorrow afternoon why spatially resolved observations still have some value, especially when we talk about scattering polarization. But here, if you're looking at the prominence or filament or something like that, you're never gonna be able to detect signals of 10 to the minus 4. So this Stokes V that you see here is completely unusable. So if you are really trying to estimate magnetic fields of, part of a Gauss or few Gauss, you actually can only rely on Stokes Q and U in this case. Okay, we can try to set it up tomorrow or this afternoon when we actually it's going to be this afternoon when we make inversion attempts. We're going to see if our code can retrieve these magnetic fields. Does anybody want to share what they did? You don't have to. No pressure. You can also do it later if you make some nice setup and so. Okay. Good. All right. So here is another example. Why did I do this? I don't know what this one's supposed to be. All right, probably just here there are now some examples of this basically, separately calculated and so on. There's Stokes V and how it changes for strong magnetic fields this time, right? It's written a little bit less nicely. No, it's fine. Yeah, because I only have one plot, so it's going to be fine. So here I have how the Stokes V changes for strong magnetic fields. And this you're used to this. This is a regular Zeeman effect. Now here we've already seen this for strong magnetic fields. There is no Stokes Q. Nothing. And keep in mind that here because this is my line of sight component of the magnetic field. Well, if I run this now, it's going to look nicer because this is going to be large. So because this is line of sight magnetic field, there is no linear Stokes Q at all. So Q disappears very quickly for strong fields. You've already seen this. Okay. So now here we are already redoing that. Sorry for the ugly legend. I can change it here. Okay, we already discussed this. I'm just going to execute the cell so that we go through that. That's fine. Right. And here you can now play. You can look at Stokes U and so on. We did all these things very, very slowly. Right. Here we are going very, very slowly through these examples. Stokes U variation, Stokes Q variation for BY. And so on and so on. Good. Now there is something different here. Here now we have, again, off-limb geometry. But now we're going to look at strong magnetic fields. Okay. What I have here is I have Stokes Q and Stokes U when I vary the magnetic field from 0 to 1000 Gauss. Now there's a little bit of warnings because I didn't use axes and so on. We can change that. I can change this here. Keep these warnings and look at this plot here. Okay. So this is a plot that is very interesting. We are off limb for 0 magnetic field. We have regular good old Stokes Q. Okay, everything familiar, everything fine. But because I made steps in the magnetic field, 200 Gauss, already 200 Gauss completely destroys scattering polarization, but is strong enough to exhibit some linear Zeeman polarization. And this is now a plot that illustrates, and note that there is no Stokes U whatsoever, right? Why there is none? Because for 0 magnetic field, there is nothing to rotate, and this field is already strong enough to destroy it. And then the orientation of our magnetic field is such that simply it will never create Stokes U. I needed a little tight layout, but you can add that yourself. What I want you to pay attention to here is that scattering polarization is not some obscure mental gymnastics that we like to think about and examine because we are bored and math is interesting. In this example here, in the case of prominence, even for 1000 Zeeman effect, even for 1000 Gauss, Zeeman effect is not strong enough to be larger than the linear polarization, right? If somehow your signal to noise was poor and you couldn't resolve these Zeeman signals, you wouldn't be sure what kind of polarization we have here. They are of the similar amplitude, right? If you can't measure a few percent to measure this Zeeman, you won't be, I mean, what I'm trying to say is basically that linear polarization signals here for weak fields are as strong as Zeeman polarization signals for strong fields. Okay, so if we can measure one, we can measure the other one. It's significant, it's important. It's not 10 to the minus 5, so we don't worry about it because we cannot measure it. It's there, it exists. Good. And then you have another plot for BZ where you will see that nothing changes, basically. Run it. There is something here. Warnings for weak BZ fields. Okay, I need to change font size here and here. Here what we get is we get that BZ for weak fields doesn't do anything to Q and U. For strong fields though, it's true that it won't change Stokes U because it's purely vertical, right? Again, there is no rotation, but I see some Stokes Q. Okay. The same as here, just the opposite size, the opposite sign. And this we already did. We have shown that magnetic field can create linear polarization at the disk center, right? And I just forgot that I told that I didn't tell you in the previous lecture that this is what we call Hahn effect in forward scattering, right? In principle, forward scattering is unpolarized, but because of Hahn effect, it can become polarized. So these are some summaries here that you should try to remember and to kind of keep in mind when you interpret scattering linear polarization in this kind of objects. So first of all, our zero level polarization. What is zero level polarization? It's the polarization in the absence of the magnetic field. It depends on our viewing geometry and on the height of the slab above the solar limb. Okay, so these are two things that you need to nail before all these things. Our all inference of the magnetic fields using Hahn effect is model dependent. What does that mean? It means that we rely on this underlying model to explain our magnetic field free polarization, and then we tune the magnetic field to get the good fit and to infer and thus infer the magnetic field, right? That's the reason why we want that. The other one is that magnetic field changes all these stories, right? And that the line of sight magnetic field introduces Stokes V, and the tangential ones introduce Q and U, but that's using Zeeman effect. That's when we have about 100 Gauss. Hahn effect itself is sensitive to much weaker magnetic field, few Gauss. Sadly, what you will see today and also more tomorrow is that when we look at the spectra of prominences and filaments, magnetic field is often neither in hundreds of Gauss, neither in fractions of Gauss, it's in tenths of Gauss, which means it's Hahn effect, but saturated. The big problem with that is that with saturated Hahn effect, we can, and now I have example talking about that. With saturated Hahn effect, we have kind of an idea of the orientation of the field, but we don't have an idea of the strength of the field because many different strands produce the same results. The only thing that can break that is Zeeman effect, but very often we don't have signal for that. So now we can maybe take some time to simulate that situation. And actually here is a example of that. So let me just explain you what is going on here. So here I'm going back to Zeeman effect. Sorry, I'm going back to the disk case. Tau is 80, so I'm relatively close to the limb. My boundary condition is appropriate. I put the slab at 25 arc seconds above the sun, so that I will go ahead. What is the boundary condition in the code? The boundary condition is your incident IQUV on the bottom of your slab, on your line of sight. So it's the boundary condition that you want to use. It's basically used to distinguish between limb observations and disk observations. It's almost always going to be either 0, 0, 0, 0 or 1, 0, 0, 0, nothing else. All the other, so it is not boundary condition for your illuminating radiation in terms, not the one that scatters, right? For example, if I'm looking off limb, there is radiation scattering, but it's not the one, it's different from the one along the line of sight, right? Here, the boundary condition is 0. It's only the radiation that scatters inside of the slab that contributes to what I see. All right? Yes. And most of the times you will do that unless you are looking at something very peculiar. For example, you're looking at the filament that is above a sunspot or something like that. In that case, you might want to make them polarized. But even in that case, it's hard for it to be polarized because the spectral line is so weak in the underlying spectrum that it's probably going to not show any polarization. So what am I doing here is I'm creating two magnetic fields, right? I have two spectra, spectrum 1, spectrum 2. Two magnetic fields with the same orientation. Does everybody agree that these two magnetic fields have the same orientation? Okay, 2100 0 and 150, but their magnitudes are dramatically different. Okay, now I'm going to plot them. I call them strong B, weak B. Look at this. Okay, I need one nice PLT tight layout. A little bit stretch for the Stokes Q. Look at this. Maybe even larger. Oh, even larger. What is it? One. Okay, good. Right. So what we see here, Stokes I is basically the same, Stokes Q is basically the same, Stokes U is very similar, Stokes V is different, but wait about that. Let's try and make them more similar. So I'm going to increase this one a little bit. Let's say 210. Now even more similar, okay? And now what I want to do here before is, now you might want to say, well, Ivan, they're not really same, right? Okay, maybe here they are the same. Maybe here they're very, very similar, but they're clearly different in Stokes V. Okay. However, what I want you to see here is that it's basically going to be the Stokes V that is determining this whole situation for me. And let's then make a little bit more complicated, a little bit more vicious example for this one. So let's try and come up with an idea where Stokes Q and U are significantly stronger than Stokes V. And for these two cases, they are the same. You know what I want to do now? I want to make an example where I have two magnetic fields that have the same orientation, significantly different strength. To make it so in order to make Q and U the same, but I'm going to position it so that magnitudes of Q and U are much stronger than the magnitude for Stokes V. You can try to do that without me. I'm just going to copy paste this whole cell. Don't worry, after this, I will save and commit to Git. So when you do Git push, you will get all this updated as it was in class. I'm going to copy paste this. I'm going to add it that, what I want to do, I think the best is if I'm on the disk, on the on the limb, and I can try with can add this, why not? Let's see what I did here. I made one example. I made it the prominence. Okay. I made one example where magnetic field is 10 along X, 50 along Y, 20 along Z. So it has some orientation. Here it's everything the same, just everything divided by 5. 5 times weaker magnetic field. 5 times is a lot. 5 times weaker magnetic field is 25 times weaker magnetic energy, right? So it has a lot of implications for the balance of this object. I plot the spectra, they're the same for Q and U. For V, I can't really tell. And then somebody might tell me, well, Ivan, just zoom. Just find the orientation of the magnetic field. Here you have Zeeman signal. From the Zeeman signal, you will find the orientation of the magnetic field because you can find the strength of your line of sight component, right? If I tell you an orientation of something and give you one projection, it's enough for you to reconstruct the whole vector. The problem is that there is noise. So let's add some noise to these observations and see what happens. I don't have to recalculate. I can just add noise and then replot. So let's add noise. Okay, sigma 10 to the minus 3, right? 10 to the minus 3 is actually very small noise for off-limb observations because this is 10 to the minus 3 in the units of the maximum of Stokes height. So what am I doing now? I'm going to do spec 1, MP, random, normal, 0, sigma, how was this? 4301. Let's see if this works. I don't know. Nice. And we do this. Then I'm going to zoom here. Plot. And what I'm going to do is decrease the range here. Increase the noise a little bit to make my point. Okay, good. This is good. So if you didn't make it to here, you can make a little break. I will give you a moment. I just want to discuss this because this is extremely important. What we did is we created some mock data by taking a model, calculating Stokes profiles, adding some noise. Amount of noise here is 2 times 10 to the minus 3. 2 times 10 to the minus 3, as I said, it seems little when you talk about the limb observations, but this is 10 to the minus 3 in the units of the maximum of this thing here. This can be very little. If your optical depth is small, your source function is already smaller than 1. So this can easily be only 10% of the disk intensity or even less. The signal to noise obviously is different. So you need to think about this when you plan your off-limb observations. So what I want you to pay attention to here is that I have two magnetic fields, which are factor of 5 between each other. So that is definitely something that we would like to know. But Stokes Q and U are indistinguishable. And both Stokes V are kind of buried in the noise here. So in this case, there is no way for me to find the actual magnetic field vector. I can only find the orientation of the magnetic field, right? Because what is the logic? The logic is we are in saturated Hanle regime, so only orientation of the magnetic field matters. The amplitude doesn't matter. For Hanle effect. For Zeeman effect, it does matter, and I hope that I can find my line of sight component accurately. And that knowing the line of sight component will tell me information about the whole vector. Because as I said, I find the orientation, it can be small, it can be long, but if I find this projection, then I can find the whole vector. That's fine. But the point is that noise will not allow me, because in these geometries, typical amplitude of Stokes V is much weaker than the typical amplitude of Stokes Q and U. And you can find these examples not only for the prominences, but also for on disk situations and so on. Right. This is very, very important thing. And this gives you one important, I would say, use for all these inversion codes that you learn to use here. It is, and Jana is here, and Han also, and other people who are involved in DKIST. I think using these codes to investigate what you will be able to detect in your observations is a skill that is very important and that will make your future proposals and your, in general research much more efficient. Because if you sit and you plan your observations and then you input, for example, expected model of your object in some code to synthesize the spectrum and add such and such noise and such spectral resolution and so on, you will be able to see what kind of signals you expect to get and whether you can detect them or at all or not. You know what I mean? So I would definitely suggest mastering SIR, Desire, Hazel, even if you don't want to invert, just to be handy there if you want to plan an observation. So this is one thing that, I've seen it in real life, that you can't know simply full vector magnetic field because there is too much noise for your Stokes V. Here, I don't even know if it's pointing toward me or away from me. And actually, later in the next session, we're going to play with inversions, where we will synthesize the model and then try to invert it back. And we will see actually what kind of noise makes sense. Because I'm now telling you that we don't see anything here, but I'm pretty confident that code can do relatively decent fit through these blue lines. Even though they're very noisy, I think you can see a little bit of V signature here. Having many wavelength points really helps with that, and we will see some stuff there. Okay. And finally, to conclude this part where we talk about forward modeling, I went to this paper, to this Hazel paper, and I prepared the example of ambiguities for you. So it's not only in these cases of saturated Hanle effect where you get the identical profiles, also completely different strands and orientations of Hanle effect can create this thing for you. So what I'm doing here is I took 4 different solutions from the paper of Asensio Ramos for something. It's again prominence, so it's 0, 0, 0 line of sight, and the line of sight is this line of sight 90, 0, 0. No boundary conditions, so it's a prominence case with 4 different magnetic fields. You see strands, sorry, 4 different magnetic fields. It's always around 25 Gauss, but the orientations are significantly different. I have inclination 40, 100, 140, 80, right? It's interesting because they always add up to 180, these two and these two here. And also different azimuths for the magnetic field. Little different, well, completely different, significantly different. And then I will run and synthesize these line profiles for these 4 magnetic fields. Okay, do it. Maybe some complaints here. Boom, 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 boom. Voila. Completely. Let me make figure much a little bit bigger. Sorry for these errors. I can rewrite it. So here I didn't really get exactly the same values, but the message I think is quite clear. So I have a prominence with 4 different magnetic field configurations, which are basically identical. This is the Hanle effect ambiguity. So they have the same, pretty much the same projection to the line of sight. Later, when we do inversions, we'll see how we can visualize this in 3D. But this is what will also happen for you. You will always get, if you do your fits multiple times, which you should, you're always going to get magnetic fields that are significantly different. Then it's up to you, maybe also according to what Graham will tell you tomorrow, it's up to you to decide what you want to take as your final solution. It should be consistent, pixel by pixel. This is so-called ambiguity. Okay, this is the end of this simple session and this synthesis here. We can stop here for the moment, and we're going to go to we're going to see how Hazel works in the inversion mode. We're going to invert for a while various things that we are going through. I'm also going to let you try and retry and so on and so on. I have already one thing that I wanted to tell you about, so I will spend some minutes coding that here and so on, convincing you of that. So I would say we go for, let's have a 15-minute break to get a little bit extra time to relax. And so let's meet here at 2:35. And then we're going to use the next notebook. The name of the next notebook, so check if you have it, is test inversion. I will open it right now. Oh, Jupyter Notebook test. I will be in front if you have any questions, and I made a mistake already. I didn't activate the environment. Okay, yeah, see you in 15 minutes. For the exercises, we used it to kind of work on something not very constrained, and then after that we are done and we can go home. So yeah, so now we're going to try, and hopefully if we have the time, if not, that we will do it differently. But let's hope that during this next 55 minutes we can fully close the story of how you invert one individual profile, and yeah, that's it. So let me set the alarm so that we know when we're done. At 2:36 and 55 would be 2:30. All right. I don't know. What is this? No, 3:30. Huh? Okay, good. So let's get started then. This was the old notebook. Let's open another notebook. I'm starting with a very simple example of inversion. So I'm going to run this to load. If there is some text, I will just tell you these things. This is for you later when you are reviewing the materials and so on. What I'm going to start with, I'm going to start with a slab at the disk center with a strong magnetic field. So it's going to be pure Zeeman regime. And we basically don't even care about scattering polarization here, just to see how the code works. Okay. So what we have here is I hard-coded parameters there, but you have here the legend, so you know which one is which one, okay? It's kind of a little bit more concise than the other example. So I have BX, BY, BZ, 500, 700, 1000. So strong magnetic field, optical depth to 0.5. Let's increase it to 1. No shift. 5 broadening. Beta, which is this artificial parameter is 1, and damping is 0.01. Gonna set these parameters and set them like this. I can just pass this array from here. This is filling factor here. I'm gonna synthesize. And then what I'm gonna do for the first time is I'm gonna fetch my wavelength grid from my model. Okay, this is where the wavelength is hiding. It's hiding in mod. Mod is our particular model, dot spectrum. And then you take the key spec1 dot wavelength axis. Right? These are all some dictionaries, objects, stuff like that. This is the number of wavelengths, and here I'm plotting it. See how it looks like? Okay, looks nice. So we have a nice absorption line. We have nice Stokes Q, Stokes U. Let me increase the fonts a little bit. I think 20 is too high. Let me do 18. Nice, right? And let me do a little good old PLT tight layout. Okay, so we have what is this? Stokes V is very strong, 10%. Q and U are fractions of a percent, right? We'll make our noise very small. We'll add the noise here just to practice, because in principle, we're always going to encounter noise. But we're going to make our noise very small, so we will be able to fit this. But keep in mind that these are very small values for the linear polarization. 2%, 5%. Sorry, 0.2%, 0.5%. Very, very small value, right? So what I'm going to do here is, and this is much less than what you would get for photospheric lines. Okay, I'm going to add some noise here, 5 times 10 to the minus 4. I can do even less. I will take 2 times 10 to the minus 4. I'm going to create this noise realization, add it to Stokes, and plot again. Nice. So I see that there is some scatter here, but still the signatures of Q, U, and V are clearly seen. So now our next step here is going to be different. Now I want to invert this data. I want to save this and invert it using inversion capabilities of Hazel, and just to see how it works. And of course, my first check should always be to see, do I get back the original values? Okay. So what I'm going to do is I need to save a certain number of files which Hazel uses for inversion. There are in total 3 files for this. One is, sorry, 4 files for this. 3 are very simple. One TXT file that contains wavelengths, one TXT file which contains so-called weights. You are kind of familiar with what weights are. We express weights here by adjusting the noise, essentially. One TXT file which contains the spectrum itself. We will see that when we invert multiple pixels, it will not be a TXT file, it will be HDF5 file. And finally, config file, which contains some of the information that we already talked about, but we will repeat it here. Okay, so what I'm doing here is I'm creating the 3 TXT files, which are the valent file, weights file, and Stokes file. And actually, let me separate all that in different cells. But I don't, use you. So for the valence, it's going to be very simple. I just take this valent array, LL, that I extracted previously here, right? Keep in mind that for my plot, I now used LL as my independent variable, right? So now instead of these stupid pixels, I have exactly the wavelengths here, which is nice. And I'm going to save that. Let's just have a look how that looks like. It's a good thing to see if you did everything correct. So I'm here. I'm going to do Sublime. This is my text editor. Open the wavelength file. It's very simple, right? It's just a header which says lambda, and then the list of wavelengths. Very easy. No big deal. Nice. Go back. The next one. Next one are the weights. Weights are what we adjust to modify how the inversion works. You're kind of familiar with them. When we want to give more attention to some Stokes parameter, we change it. Here, in principle, you can adjust weights according to the wavelengths and according to the Stokes file. So you have wavelength and Stokes dependent weights. I'm just going to set everything to 1 here. Okay. Also, I don't care about it because later in the Stokes in the file which contains my Stokes information, I'm going to keep the noise, and I can always adjust that noise instead of adjusting weights, and it's going to have the same effect. If I want to have something matter more, I artificially decrease its noise. Okay. By noise, I mean noise level, not the noise amount. Right? We never know noise amount. If we did, we would remove it. Right? We only know the standard deviation of the noise. We don't need the exact one. And finally, I write down the Stokes profiles. Actually, let's see how this weight look like. Very simple. It says weight I, weight U, weight U, weight V, 1, 1, 1, 1, 1. Easy peasy. I can create this one and never change it anymore. And then finally, profiles. I'm going to open a file here, which is called 1080 test Stokes 1D. 1D is the extension that Hazel uses for individual spectra. So if I'm inverting only one spectra, it's going to be TXT file with extension 1D. And here I'm writing first the line of sight down. So you should try not to mess this one up, right? In real life, you would be preparing this in a completely different situation. You would be browsing through your observations and preparing these files. So just now, because we are playing with this forward-backward situation, that we are doing it this way. So this is our line of sight here, 0, 0, 0. Boundary condition, 1, 0, 0, 0. So we are the disk center, right? So that's why it is like this. Then I write SI, SQ, SV, UV, sigma I, sigma Q, sigma U, sigma V. And I write down the Stokes vector, which I created up here, right? Where did I create? No, I created it here, right? And I write down the noise. Noise is just noise level times 1 for everything, right? So if I do this, and I open this file, 1080 10 Stokes 1D. This is how it's going to look. It's going to have a header for the loss. It's going to have loss, line of sight. It's going to have a little header for boundary condition. It's going to have boundary condition. Little header for Stokes profiles. Let me just disable wrapping. And it's going to have I, Q, U, V, and then noise values here, 2 times 10 to the minus 4, written in very high precision. Because we chose it that. Cool. That was one chapter, right? The next chapter is to set up this ini file, which contains the configuration. Okay. I have it here named conf Zeeman ini. So let's open that one. Right. It's pretty self-explanatory, right? It has few sections. One section is working mode, where you set up some main parameters. Next one is spectral regions, where you specify the things related to your spectra, and next one is atmospheres. Okay. Let's see what happens here. I'll try to explain you every of these quantities. So in working mode, you first put what is the output file. By default, the code will put all the results into HDF5 file, right? It's a file format which packs these things like little objects, like in a way like fits, you could say, and then saves them down, and then you load them and you get them. Number of cycles. Oh man, what are these cycles? The cycles, I had cycles in SERV, which were related to number of nodes. So I don't know why the Hazel needs it. Well, in this case, we can have multiple cycles because we can choose to fit, for example, first only Stokes I, and then maybe QU and V later, maybe because thermodynamic parameters are typically already determined very well by Stokes I, and we can also change and have, for example, only fit in order to obtain optical depth, broadening, and the velocity from the Stokes I in one cycle, and then only magnetic field in the other cycles, right? There is maximum iterations. This can be useful if you want to make sure that your code never wanders away, never lingers, and so on. It is good to limit, just make sure that everything is fine. And relative error is another parameter that you, even if you delete these, nothing is going to happen. The code is going to revert to some default values. Relative error is at which kind of what relative error between these two consecutive values of chi-square the code will use to break the iterations, right? So if the chi-square is not changing by more than 1 in 10,000, 100,000 actually, the code will just stop, even if we didn't reach 20 iterations, right? So this is something that I use to make sure that my code is not running too long, because maybe sometimes it's stuck and it won't be able to fix. Okay. So topology is going to be here in spectral regions. I'm going to explain you what it is. Very important keyword. So first of all, we name our spectral regions here. Each of we can in principle fit multiple things, right? Here, what I'm going to do is I'm going to have only one spectrum. It's going to be named spectrum 1. So in the results, we're going to have keyword spectrum 1, which describes these fits and observations. Topology. In principle, whenever you invert simpler things, you're going to call this you're going to call things like this, chromosphere 1. It's just one slab. Marta, if you want to fit multiple ones, you do this. This would now be 2 slabs with 2 consecutive, where the radiation is formed in one slab and then enters another slab and so on. In principle, it can even go like this. Right? This would be photosphere, then chromosphere 1, then chromosphere 2. Photosphere comes from this hard-moded SIR extension that not extension feature that Hazel has, but we're not going to go there right now. I'm just going to do it like this. Stokes weights. This is what code is going to revert to if you didn't provide the file. Line of sight. This is what the code is going to revert to if you didn't put them in your observations. Boundary conditions the same, and so on. But here you provide the wavelength file, wavelength weight file, and the observation file that you just created. You typically create them once for one set of observations, and you don't touch them anymore. They can stay like this. Okay. And here there are some additional weights that are now defined for multiple cycles, right? So now I have weight for first cycle and for the second cycle. And these weights are going to be multiplied with the weights that you have provided in your file here. Okay, so it's a little bit redundant, but it gives you a lot of flexibility that way. Okay. So here, what does this mean? This means in the first cycle, I only fit Stokes I. In the second cycle, I fit all of them, starting with the values that I have reached in the first cycle. Mask file doesn't make any sense now, but it will allow you, when you have huge field of view, and you don't want to fit all the pixels, you can create a mask file that only fits some pixels. Cool. Now here is atmosphere. We describe our chromosphere. We name it chromosphere 1. It's going to be named chromosphere 1 in the output. I can also name it, I don't know, sun in PlayStation, whatever. Spectral region is the spectral region that we created here. Height, we have to specify height here. In principle, if you're above the limb, you will know how to do it. Right? If you're not above the limb, then you will have to figure out something, right? Here we put which line we want, wavelength range where the line counts, and the reference atmospheric model. What is a reference atmospheric model? It's a model that contains starting value of the parameters. If you were using photospheres here and things like that, you would have these complicated models like in Hazel, like in SIR and Desire. However, we don't. We only have a chromospheric model. called model chromosphere 1D, and it's literally just numbers. These are the starting values our model is starting from. Bx, By, Bz, tau, V, delta V, beta, A, and filling factor. Right. Cool. Then we can define the ranges in which we want our physical parameters, right? So I can say I want magnetic field to take values from -2000 to 2000 in all these three, right? I'm not expecting anything more than that. Optical depth doesn't make sense to make it too large or too small. Velocity doesn't make sense to make it too large. Broadening also doesn't make sense to make it negative or below some certain amount or larger than something else. Beta, I'm giving it some flexibility here, but it doesn't matter because later when I define which parameters are fit in which cycle, I'm not going to allow it to change. A is in this case the damping. It cannot be negative. It shouldn't be larger than 1 because it will be some really weird profiles then. And filling factor also, I'm going to limit it here, but I'm not going to fit for the filling factor. And here finally we have nodes. They're called nodes just because Andres wanted a generic name to call them. They would in principle be nodes if we also use the SIR functionality here, but we're not. So nodes are literally just which parameter am I fitting in which cycle. Okay, so here this says I'm fitting in first cycle, I'm only changing tau, V, delta V, and A. The second cycle, I'm also changing Bx, By, Bz. I'm never changing beta. I'm never changing filling factor. If we had the photosphere, then it would make sense to have 4, let's say 5, 7, 9, and so on and so on. But that would be significantly different because then here we would have photosphere 1. We're not going to go there now, maybe later. If you want to try, you can use this, freestyle hour to play with it. So I'm going to save this one config file now. And now this is all that we need to run an inversion. We need the config file. We need these three things with the data, and that's it. So I'm back here. This is how we set up the inversion. We create a so-called iterator. Okay. Iterator is an object that does the inversion. And iterator can be created also using MPI. Now it doesn't make sense to use MPI because MPI here works by separating pixels. If you want to invert one spectral line, one spectral profile, it's always that you only need one thread. Okay. What I'm going to do is I'm now going to create the model, which is going to be created in a slightly different way than before. It's going to be created from the config file. The working mode is going to be inversion. I'm going to set verbose is the keyword that tells me how much output I'm going to get, how much information about what's going on. I'm going to set it to 3. 3, I think, is the highest level. This is actually not important right now. This is only important in MPI. And finally, there is this thing with randomization equals 1. Randomization equals 1 is very important keyword, and we're going to use it very, very soon. It allows you to automatically run multiple inversions with different initial conditions in order to probe your ambiguities and degeneracies and things like that. Okay, what I'm going to do now is I'm going to pass this model here to the iterator, and I'm going to run the iterator, right? I made it like this, a little bit more complicated, because later I will show you, tomorrow I will show you that you can literally just copy paste this to a Python file and run things in MPI. Literally, you don't have to change anything. You just say MPI exec n equals, and then how many cores you have, and you run a file and it works. Now I'm going to run this. And it's outputting a lot of things here. And currently it's outputting a lot. And it's now, scrolling here. It's more and more text. So we are waiting for it to be finished. We are waiting for this. Okay, this asterisk here disappeared, which means inversion has been done. So here, Hazel will output everything for you when you put it in maximum verbose mode. To say which version is that, it's always 1.0 though. It tells you which configuration file you use, what it read from your inputs, and so on. It says using 2 cycles, 20 max iterations, not using randomization, stopping when relative error is below blah, saving all cycles false. So it's only, by default, it's only going to save the last cycle. You can change this. adding atmosphere, blah, blah, blah. And then here comes what we care about. Here is cycle 0, which is our first cycle, right? It tells you the weights, so you can verify that it's the way you wanted it. So we're only fitting Stokes I in the first one. There is no regularization, of course. There is no regularization because there is no atmosphere, so that there is no depth-dependent atmosphere. So forget about that. And what is important for us to look at here is to look at chi-square. We're going to see how chi-square is decreasing, right? And we are hoping to get chi-square equals to 1 because we created the model. We know our model is correct. We created a noise. We specified correct noise. So we hope to get chi-square equals to 1. We'll see if we reach it. We start from 216, which is already not bad. And then it shrinks 129, 129, 129. Never going to work out because it cannot fit simply because there is no magnetic field changing. The magnetic field influences something. So the code is moving to cycle 1. Now in cycle 1, it's fitting for everything. And it starts, chi-square is 375. 375, 287, then jumps to 3, then to 1, then to 1, then to 1, and then it stops because it cannot change anymore. So it's already very interesting to analyze, for example, why chi-square couldn't be 1 in cycle 1, why it jumps like this. There is a lot of numerical and nice, statistical and so on subtleties. I will leave you to it, and I will leave you to experiment with them and figure them on your own, and maybe come and talk to me if you want. What we're going to do, we're going to see if we got what we expected for, if our fit is good. I'm going to familiarize you with how the output looks like. So we open the result as a H5 file, okay, using H5 package. And immediately the first thing that I do when I do that, because I know it's some sort of dictionary, I look at the keys. When I run that, the keys are chromosphere and spectrum. The chromosphere is where your code is going to keep your inferred model parameters, errors, everything else. The spectrum is where it's keeping all the things needed for the spectrum, original observations, and the best fit. So we immediately have everything here to compare and see whether our fit is good or not. I'm going to look at the it's actually not going to keep the original observations, I think. Yeah, we have to fetch them from our original file. So what we have here is we have a spectrum with, we're going to look at the keys of the spectrum. It has something called AIC, BIC, chi-square, Stokes, valent. Valent is valent. Stokes is the best fit Stokes. Chi-square is chi-square, so it's giving you chi-square, so you can look at it. And this is really chi-square, meaning observations minus the fit divided by noise, squared, summed, averaged, and valent. So it's compatible with what you would calculate on your own. AIC and BIC are two measures of quality of fit that also take into account model of parameters. They're called Akai, like Akai berries or acai berries, information criterion, and Bayesian information criterion. They're somehow similar to chi-square, but modified so that simpler models are better, right? You might want to use it if you fit your profiles with multiple different models of different complexity, and then you want to decide which one is better. Right now, for us, it doesn't make any sense because we're keeping constant model complexity. And then in the chromosphere, you have much more keys. You have all the different physical parameters, and then their errors, right? We are interested at Bx, By, Bz, and their errors. And then, basically we are mostly interested for the in the magnetic field, but also maybe velocity and so on. Okay, I'm going to name one array, call it fit. I'm going to copy it as Stokes from the keyword spectrum. And when I look at its shape, it's going to be 114201. What does that mean? First one is for number of pixels. We only inverted. Let me actually write that one. Shape is number of pixels, number of randomizations, and number of Stokes components, number of valence. just going to reshape it here because I'm going to be using one randomization here, but I don't have to do that. Actually. It's fine. Then we're going to compare the original fit and obtain fit. I know that my chi-square is 1, so fit is probably great. Okay, no, it's not because I didn't reshape yet. Yes, fit is absolutely great, right? The code did a fantastic job. Now, of course, the next step that we typically want to do is we want to print out the parameters. This is where parameters are hiding. They're hiding in the chromosphere, then the name of the parameter, then they are also oriented like, you know, this is the number of pixel, number of randomization, number of, I don't know, we'll have a look at it later, what exactly this is. And when I run this, amazing, look what I got. I got bx and by that have opposite sign from what I input. So this is almost 500, this is 500, this is almost minus 500, this is 500, minus 700, 700, 1000, 1000, 1, 1, good, 0, 0, 5, 5, 0 0.01, 0 0.01. So everything is good except bx and by. Yet fit is flawless. How is that possible? Yes, exactly, Marcel. It's ambiguity. So even in the simplest possible case of the magnetic field, when we have the Zeeman effect, there are two solutions that are completely identical, mathematically identical, not degenerate, not poorly sensitive, identical. And tomorrow morning, we're going to be talking about resolving that ambiguity. It cannot be done just by looking at the Stokes spectrum. You need to invoke some other sort of information. There are many kinds of that information. So this basically, I cannot tell whether you're standing like this or you're standing like this. So we can say, well, let's assume that first person is standing like this. So then we flip everybody, you know, like this. Or you could say the minimum energy is if everybody's like this, and so on and so on. It's up to you to decide. It has nothing to do with the Stokes spectrum and inversion. This is now gives you a lot of power to do fits and to interpret any 10A30 profile that you want, or D3 or something like that. So we're gonna carry on and we're gonna see if there is a way for us to recover these physical parameters here. And the first thing that I would do here is I would print, I would do multiple randomizations here to try and get multiple results and see if I can, you know, get both ambiguities just to be sure that everything, I mean, not just to be sure that everything is fine, just to, you know, see that we can also get the original values here. One thing that you might want to do is you can also output the error, right? Error is not error, it's uncertainty. It's what code estimates to be uncertainty. That's certainty equals, and then we can say result chromosphere 1 bx is called, we have it here, bx error. Okay. Oh, what's the problem? Ah, because I removed the file. Did I remove the file? I didn't. What did I close? I don't think I closed it because it's. I did. I closed it. Thank you. Okay, let's not close it here. Close it here. Typically, remove these files because H5 is a little bit finicky in that sense. And I want to save in everyone. Let's not close it. Good. Let's open it here. Because the error 3 arguments for 2 dimensions. How about this? Okay, so this is what code infers for uncertainty. It infers very, very low uncertainty because the fit is very, very good, but this uncertainty is obviously not realistic, right? So be ready to have, for most of the codes, to output uncertainties that are absolutely not very meaningful, right? So I also just finding alternate ways to use this. But it's good to just have it, How V delta V and uncertainty for A is always huge because it's such a weak parameter. Okay. Now let's fit a different configuration. I will go back to this and I will show you how to do multiple randomizations and so on. But let's fit something completely different. Let's fit a prominence. Okay, to see that maybe we'll already get problems even when we take a simpler model. So what I'm doing everything basically pretty much the same as I did before. I changed my working mode back to synthesis. Did I delete file? No. Let's delete the file. I do everything pretty much the same. I go back to the synthesis. I synthesize the prominence, right? I create it with some, magnetic field. This is weakish magnetic field, but very typical of prominence, like 3 - 4 7, 0.5 optical depth, 0 velocity, 8 broadening, and so on and so on. Really nice. I set these parameters. I synthesize. I plot it just to make sure if everything is fine. It's fine. I have like 1% in Stokes Q. Or let's add a little bit of tight layout. Right. Nice. I have typical Stokes I. I have linear polarization of what is this? 1% here, 2% here. Stokes V incredibly weak, right? Like what we saw before. Gonna add a little bit of noise here, right? Let's actually, let's do it a little bit different. Let's increase line of sight magnetic field a bit to like 15. And let's add very little noise to data, like 10 to the -4. And plot. And it's gonna be nice. We see a lot of scatter in the continuum because continuum is 0, so there's a lot of scatter. I need this. This is my input data. And now I go through a little bit more concise process of, writing them down. I'm going to overwrite the files. I'm again going to call it test. So keep in mind, if you want to go back, you have to regenerate them for the filament case. Or we can just call it prom. Test prom. Test prom. Test Stokes prom. Create all that. And then I have conf prom ini, which is my configuration file. I need to change it because I just changed these things now. There it is. I now have 3 cycles for some reason. I will explain you why. We can go back to 2. This is not like you have to do it this way. I did this at some point, and then you can change it and see if it works for you. I'm just gonna add this, underscore prom that I had before. And I also needed it. No, it's fine. Yeah, this is my generic name for this, number of cycles 2. Actually, no, let's go to 3 just to show you why I did that. I did this because I wanted to go only Stokes I in first cycles, QU and V without I in the second cycle, and then all of them together. And for the parameters, I went thermodynamic parameters in the first cycle, magnetic parameters in the second cycle, and all of them in the third cycle. So just something for me to try. And look how I limited the magnetic field and everything. I really anticipated it to be weak, but we don't have to do that. We can increase to larger magnetic field. But this is something that can, in principle, help you converge if you limit your magnetic field. So, cool. I'm going to run it now. Now, again, it's going to output a lot of things here. I changed verbose to 1, though. So here we just wait. We don't have a lot of output. I don't want to interrupt it now because it's gonna mess up with the files that are already open. But yeah, let's just wait. Did the first part work for everybody? It's done. I'm doing the same thing, looking at the output, comparing the output and the fit. Fit is really good. Okay. Looks high, perfect. Looks Q, perfect, perfect, perfect. I plot in the comparison between parameters, and they are fairly similar, right? 14.94 minus 4 minus 7.7. Okay, so now Y and Z are flipped. But keep in mind that Y and Z are now our plane of the sky magnetic field, right? We are in different viewing geometry. X is pointing toward us, and these two are now flipped, right? So we again somehow got the ambiguous solution, right? All the other things are pretty fairly fit, and that is pretty fine, right? So now I can try to do multiple randomizations, okay? What I'm going to try to do here is I'm going to set randomization to 5. See what kind of results I get here. But let's do it in a new cell. Okay. Our fit here. This. We remove the file. Let's remove the file. Nice. And then here I'm going to say insert cell below. I'm going to say, let's see how randomization works. So. Okay, copy paste from above. You don't have to delete all these models. I'm always doing this delete just to be like super safe, but you don't have to do that. Do here is I'm going to set randomization to 5, for example. I set verbose 2, so we still get some output. I'm going to run it, and now it's going to take some time. It's spitting out chi-squares only. It's not spitting out the values. So what I'm going to do now is I'm going to let this run and run outside real quick and get back in a second. And you folks let me know how if it works for you. We have 15 minutes more, which is just enough for us to see what happens here. This code is not the most insanely efficient because it needs to recalculate these, all these polarization components and so on every time, and so et cetera. So it takes some time, and then it's doing that in multiple cycles and so on. But we can kind of gauge how far it made. See, chi-square here is even lower than 1, really fitting really well. Okay, we made it to 3 randomizations. We let it work a little bit more. Meantime, here to analyze the data. To analyze the data, well, I need to pull the Stokes out. Right. Right. I won't be reshaping it because it will be different. It will have different shape now. I need to plot multiple different solutions. What I'm going to do is I'm going to go to the previous one here. Still working. This one is not really fitting. Like, okay, maybe depends on which cycle it is. Okay, it's done. See, at the end, it will output this little thingy for you. So for 5 randomizations, 3 cycles, it took, what is it? 4 minutes, 20 seconds to calculate. Good. And look at now, my fit has a different shape. It's 1 for 1 pixel, 5 for 5 randomizations, 4 for 4 Stokes parameters, and 201 here. Okay. Plot it now. So I'm going to use this way with talked out before. I'm going to grab the wavelength. Something like this. We have LL already. See. So what I'm going to do here, I just want to plot. I will first plot my observed spectrum. It was called Stokes, I guess. It was called Stokes. And then I'm going to plot all the different fits. Got it. Go. Oh, sorry. Plot LL Stokes I. And here I'm going to plot, and I'm going to plot that one with this. Here I'm going to plot LL fit 0 I, no, sorry, 0 JI. This works. What do you, Stokes I. Okay. Okay. For each axis, plot first Stokes, that X, and then loop through fits and plot this maybe a bit better. What is not subscriptable now? Fits. Fit, yeah. Okay, now what's the problem? 4 is out of bounds. Index 4 is out of bounds for axis 0. Because I'm looping over 2. Oh my God, man, why am I so bad? All right, so you can see here that not all the fits were really good. Okay. So we have multiple solutions, and actually only one of them is really good, which is not something that I would expect from the get-go, but yeah, unfortunately, this is how we ended up. So we can now redo that and so on and hope to get more. But in principle, you can now select between these randomizations and choose the ones that you like, keep them, analyze them, and so on and so on. Okay. Right. Okay, good. Well, now let me see if this example here will work. No, doesn't matter. Okay. What I want to show now is I want to redo this example of randomizations using the, actually, you know what, maybe that's not exactly what I want to do right now. I want to show you one more thing, but we have very little time. All right, let's go to this example here. Okay, so this example here is on disk, medium magnetic field, and fairly low noise level. Okay, so let's scroll down under this chapter which says ambiguity and synthesize the model. And this is how that model looks like. Okay, I again have a fair amount of noise, but Stokes profile are recognizable, and I think we are all expecting to see basically Hanle profiles, right? The magnetic field is quite weak, 10-ish of Gauss. So actually what we will see is Hanle effect, but saturated with Hanle. And I want to see what we get when we try to fit this. Again, I'm saving it in these files here, and I'm rerunning. Well, let's see, what am I rerunning? I'm going to save these things here. I have another config file, which is called conf test on disk. See if I have it here. Don't. Right, so let's I'm gonna copy it from front one. Sorry about this. This was a little bit and I'm also gonna commit it so that you folks can immediately see. Actually, you know what? We can do this one later. Let's redo the prominence example with a larger amount of noise and see what changes. And I'm gonna push this on during the break. So we're gonna leave this example here for later. Let's go back for the prominence example and see what happens when we increase the noise. So all the way back to this example here, right? Where we had Stokes IQUV. Okay. What I want to do is I want to decrease a little bit the magnetic field. I will decrease this back how it was before, right? Stokes V is very small. I'm gonna say that noise is 10 to the minus 3. Okay. Now when I calculate it, it looks like this. I get Stokes Q, Stokes U, I see them very clearly. Stokes I, of course, see very clearly. Stokes V is a mess, though. There is nothing here. So let's see what does the code do in that way. I create these things. This is old example. This is the prom one. I run it again. I run it again here. I think I know what my problem was. Do this again. The problem, I didn't delete the file. Yeah. Try again. Running. Okay, it's done. 20 seconds roughly. I load the data, I plot it. I is quite well fit. Q and U are reasonably fit. V is nobody knows. Okay, so this is already noise playing trick on us and having, complicated configuration. Let's see what we get. We get complete nonsense. So look at this. A is great. Thermal velocity is great. Line of sight velocity is great. Optical depth is great, but magnetic field is completely off. Off by a factor of, what is this? More than a factor of 30. Okay. Except for the BX. BX is quite well constrained. Why is it well constrained? Because the code knows that it cannot go above this noise. It cannot make a huge magnetic field here. But for these two, in the plane of the sky, it's completely messed up. It got something that here looks good, but here it's completely off, right? We are kind of, it's good direction, right? Along good direction, but the magnitude of the profile is completely wrong, right? What we can do now is we can see if decreasing the noise will help it. I'll turn this verbose here to 3 so that we can see a little bit better. Let me go back, return this to, for example, 5 times 10 to the minus 4. A little bit clearer, not much clearer though. Save this again, rerun. I'm getting a lot of nice output here. Up. Okay, let's just look at this one and we go to break. You see that the code cannot quite fit everything. The chi-square is stuck around 5. Good fit, but not really good fit. I didn't delete. No, it's fine. I open it. I plot this the fit. It's again. This is something that you can maybe tune a little bit by changing your weights and so on. We can try to do that later. Again, output. Much the same, right? The output the same. I don't like that. Let's redo this. Okay, we can take a break now if you want. I want to play with this a little bit more. Did we want to have a Q&A session? Is Rebecca here? How long break are we supposed to have? Half an hour now, right? Let's have half an hour break. If there's Q&A session, if there's Q&A, we can do Q&A. If not, we can sit. I have one thing that I want to try to show you. So I will try to, hack it in the real time, and you can try to do your examples here. But this is basically the goal here, is to play with this a little bit, play with the noise. And there is one more thing at the end of the notebook that I want to show you, which is how to visualize these different magnetic fields that you will get as the solution. Okay. I just want to redo this one now. Ah, there you go. This got messed up. Okay. Didn't actually run. Here there is a little bit less noise, and now we rerun. Verbose equals 2. If you set verbose equals 2, you just get chi-square for each iteration, which is probably the optimum way to fit. Nice. Again, it can't quite fit 1. I don't know why. Wow. The height, maybe. Make sure to check when you do this whether your input height is the same as the height in the config. Okay, it is. I updated these notebooks if you want to download them. Point. Let me see what is there. Mhm. And run a bunch of randomizations here just to see what happens. we want to talk about now? I want to show you what I set up here. What I set up here was, again, a randomization. 10 different randomizations. Verbose 2 so that we can track how chi-square is decreasing. I also went and sorted out some things to streamline the inversion a little bit so that it doesn't wander around too much. I decreased these ranges a little bit because we know that we're in prominence regime. We don't expect hundreds of Gauss and so on. And I also increased the number of maximum iterations to 50. The reason for that is because the code sometimes, when you give it multiple randomizations, starts from some very weird configuration, right? Very high tau, very high velocity, something like that. And chi-square is huge. And it needs some iterations to converge to get down to the good fit. And now we're going to inspect that a little bit. So here in this cell, I rerun everything. I took 10 randomizations and I ran this. And you can see here that chi-square is dropping down for most of these. We're going to expect it now, actually. So what I'm doing here after this cell is I'm opening it again. It has 10 randomizations now. There's 10 values. But now before actually looking at them, what I'm going to do is I'm going to look at the chi-square. Okay? So I'm going to say chi-square results is mp.copy results. Let's close the Discord. Results spec1 chi should be chi-square, right? No, it's a result. Sorry about that. And then I'm gonna go chi-square results shape. And I get what? I get 1 for 1 pixel, 10 for 10 randomizations, 2 for 2 cycles. So let me print right. Okay, most of these went well, right? Chi-square is very low. Few of these are not good, right? In principle, what you would do if you were doing this for your research, you would discard these inversions because they didn't converge well, and you would use these other ones, right? So also if I plot them, these 10 different fits, I will get 2 that are bad, that are very, very bad, and then a lot of these that are really, really good. When their Stokes V are a little bit different, but Q, U, and V and I are really good, right? I'm gonna delete this here. So what we can do now is we can actually try to output these physical parameters somehow. What would be the most concise here to do that? Well, I can look at I can look at one parameter. I can look at the magnetic field, for example. Where was I? Here. This, so let's say print result chi-square 1 bx for it. I need to do MP squeeze here. See, it gets different results. Most of these are probably good. All these that are similar with each other. But some of these are bad, right? We can look up here and see which is bad. The last one is bad, and the second to last one is bad. So this one is bad, and this one is bad. The other ones are kind of okay. Right. So now what you would do is you would visualize this. You know, you can look at what your BZ is, BY. It changes, it has similar magnitude, but it changes the sign. This is because in some case we get one solution, the other we get the other solution. Same for BC, right? So I don't remember what I wanted to show here. So we can go and look at the ambiguities, and there is an exercise here which I'm not going to run it right now. We might run it right now, which shows these exact same thing with randomizations and so on. What I want to show you here, so I will skip it right now, right? What I want to show you is how to do this. I'm going to plot these vectors in some sort of coordinate system in order so that we can see how our randomizations look like, how our ambiguous solutions look like. Okay, so I'm just going to jump here. Okay, I'm skipping over something. Basically, all this section here was redoing the same thing again. You can rerun it on your own if you want. What we have here is that we're going to run this same thing again. Let me see and make if there is anything that is messing it up. Okay. There's a little bit of. Okay, let's try and see what how I can do this. So let me create first this array, original parameters. Or you know what? Let's actually rerun this thing here. Why not? We can do that and just yeah. So what I'm doing here is I'm creating another model which has magnetic field of 20, 50, 20. It's on disk. I committed the file conf on disk. So if you do pull, it will come down. So we can generate this data set identical to what I did before. All right, let's keep it a little bit simple. Okay. So what I did then is I prepared the files here. And I inverted it with 5 randomizations, okay? Let's run that again, and then we're going to see what happens underneath. In mind, I'm going to visualize that in a bit. But I didn't delete the output file. Sorry about that. Delete this, and then we rerun the ambiguity exercise here. They'll go to this file conf on disk, test on disk, and I'll tune up just this maximum number of iterations a little bit, and that's it. And I'm going to rerun it now. I'm going to explain, while this is running, I'm going to explain you what I want to do after this. Running, it is nice. So what we're going to do after that, we're going to look at these plots again. They are now on disk, so they're going to look like filaments. Some of these fits might be bad, some might be good, so we're going to eliminate them. I'm going to output them one by one. Okay, it's going to look like this. We're going to look how they agree with the original ones. We're going to plot the fits. We already did that. We don't have to redo that again. What I want to do is this thing here. I'm going to make arrays, and we're going to try and plot. I'm going to make I'm going to make these solutions as vectors, and I'm going to try and plot these magnetic field vectors here, and we will see what comes out of that. Let's see how this notation here works. I'm just gonna say we will take 2 solutions and plot them, and we will see what we get. Let's just put it that way. But to do that, I need to move this thing here. Let's see how our inversion is going. So it's done. It took 1 minute and 20 seconds. Print it out. 5 randomizations. Okay, I'm reshaping it here. Let's just run it as is. We rerun the plots. Okay, all the fits are pretty good. That is good. Okay. Now I'm going to plot the results. Okay, this is exactly what I wanted to get. What we have here in this block is I have for each randomization original parameters and then inferred magnetic field. Keep in mind that even though all fits are great, All fits are really, really good. There is some noise, but they are still good. Okay, and they're all the same, pretty decent. My solutions for the magnetic field are completely different. Okay, the reason for that is Hahn effect ambiguity. Different magnetic fields pointing in different directions with different magnitudes in saturated Hahn regime result in the same ones. So let's plot now a little bit how they look like. What I'm doing in the next one is I'm just making sure that I'm not insane, that they are all agreeing very well. They are all agreeing very well. Okay, I can delete this one here in order to keep it a little bit cleaner. Let's try and plot these different ones. So I'm going to go and plot two different solutions. Let's plot, for example, first two solutions. So this is first one, second one. What I'm going to do here is this is bx, by, bz 1, or let's call it bz 0. Okay, bx, by, bz 0. And I'm going to also make one more, which is going to be 1. X1, bx2, bx3. 1, 1, 1. 1, 1. Then I'm going to pack them as two vectors here. I'll do it like this. Sorry, should have updated this. bx0, by 0, bz0, and here we have bx1, by1, bz1. Then I'm gonna reformat them like this and gonna plot them and it will hopefully work. One extra. Okay. bx2, okay, pretty bad. Yeah, thank you. And the problem, field elements must be 2 or 3, tuples got 0. Vectors NP array. Like this, maybe. Wow. Up here. Okay. See what the problem is. So this needs to go like this. Okay, amazing. Good. So these are the two ambiguous solutions and how you can visualize them. See that one has strong magnetic field, the other one has weak magnetic field. They're pointing in roughly 90 degrees. We can't really say. The proper thing to do now, let me increase this figure a little bit. Okay. The thing to do now would be to find your line of sight. Your line of sight is defined by the theta angle, as always, which is 70 degrees. Here it's not 90, it's not 0, so it's hard to align it over one axis. Project this to your line of sight and see how they look like, right? But now we can change. We can look, for example, okay, what happens between these two? Look, one more ambiguous solution. One more ambiguous. Okay, these two are fairly similar, and so on and so on. Maybe we can even pack up all of them. Let me see if that is possible. Yeah. If I do something like this, say B is MP squeeze. No, we do like BX, BY, BZ. Squeeze this. This is going to be MP squeeze this. gonna be MP squeeze. And then here for vectors, I'm gonna make it a little bit more complicated, hopefully. No. Vectors is 0, 0, 0, and then I'm gonna say bx 0, 0, 0, dy 0, 0, d 0, 0, 0. Nice. Then I'm gonna add the other ones here. And here we say 1, 2, 3, 4. 1, 2. There's probably a better way to do this with append or something like that, but see how this turns out. Oh, come on. This is 1, this is 2. Oh, come on. Too many in this array is one dimensional, but 3 were in this. Oh, which one? Oh, wow, okay. A squeeze will remove that. 0, 0, 0, 1, 2, 3, sorry, 3, 4, 1, 2, 3, 4. Here, 1, 2, 3, 4. Cool. There we go. 4 different ambiguous solutions. This is typically the most that you will have. You will typically have 4, right? And typically when you project them to your, we can't do it right now because of our inclination angle is a little bit weird, but when you project it to your plane of the sky, what is the plane of the sky? It is a plane which is perpendicular to your line of sight. When you project them there, they will roughly make a cross, right? And you will typically have 2 strong ones at 80 degrees from each other and 2 weak ones for 80 degrees of each other. And then what happens, and you will hear more about it tomorrow from Graham, is that you then are left to decide what is happening. One way to resolve this is to use lines that are not saturated with your fields, which is hard. You can't always do that. Sometimes what you have to do is just live with this and choose, right? And typically we don't even think about 80 degrees, 180 degree ambiguity. We just say, okay, I know that these and these are ambiguous. I don't even care about that. I leave it to something else. But how to deal between the weak one that is pointing here and the strong one that is pointing here? Well, for that, I maybe make some considerations concerning my object and so on and so on. We will maybe mention it tomorrow when we are done with everything during the talk. Okay, so now what I wanted to do, but it will take me some time to set it up. So what I propose, everybody can just make their own example and play with it, change the noise, change the number of randomizations, try to visualize this and so on and so on. Practice your coding and Hazel skills a little bit. I'm going to tell you right now what I'm trying to do, just to not make it too mysterious. I want to try and see how the number of vagrant points helps us retrieve the magnetic fields. Because very often we think that, okay, in order to detect magnetic field, we need to have noise which is lower than the highest signal. But I have some hunch that if you have many vagrant points, it will allow you to compensate for high noise. So I want to see how reliable our fits are, for example, at the disk center, at Zeeman effect, if the noise is there on the limit. And you maybe don't understand exactly what I'm trying to say right now, but I will try to set up an example and to get it working right now. So I'm just going to paste it to the end of the notebook and work slowly. And I suggest you try to make some of your own example if this is something that you think will be useful for you. If not, you can hang around. When Rebecca comes back, we're going to ask if there are any questions and do a little bit Q&A. And if you want me to, come and help you set something up or something is not working, just shout and I will come there. So we can work in peace next like half an hour or something like that, and you try to get these things going. And tomorrow we're going to work with the real data. So now try to get comfortable to get these things to work, and run your own examples, set up your own examples, and so on. Do git pull so that you are sure that you got all the files that I created during the break. Okay, so this was kind of something that I was going for. Okay, let me show you this. So I made a case where we have a on-disk filament, strong magnetic field, so Zeeman regime, inclined magnetic field, very, very horizontal. So X and Y are 1,000 and 500 respectively, Z is only 150. And when you plot that, you get the Stokes IQ/UV, which are roughly 1% each, right? Typically, your intuition would be, I need signal to noise lower than 1%. And this is even lower than 1%. This is 0.5%. Your typical intuition is, I need signal to noise lower than 1%, or actually better than 100. So noise smaller than 1% in order to see and characterize magnetic field. But keep in mind that our fit and characterization is not done from a single point. It's done from a series of valence points. So what I also did is I created this very finely sampled in valence to kind of try and emphasize this. But it will work even with less valence. I go and I add noise of 10 to the minus 2, huge noise. 10 to the minus 2 is really poor in solar terms. And when you plot it, you get something like this. Okay? There is very little signal, but you are kind of seeing it, right? You kind of see that there is some sort of V here. You kind of see that there is some sort of U here. Here you don't see anything. And then I let it fit. I pack it, I let it fit, blah, blah, blah. It works, it works. I open the result. I plot the fits. Fits are looking like something. We don't know if that's good. I plot the outgoing solutions, and they're very good compared to the input. So I'm only missing a little bit in BY, right? 600 versus 500. This is almost the same. This is almost the same. These are all the same because they're inferred from Stokes I. With this huge amount of noise, I still get good results. The reason for that is that your valence is so nicely sampled that it compensates for some of your lost signal to noise. This is something that has been bothering me for a while, and I kind of felt that it has to be this way, and now we checked it. You can try this with various examples and various fits, and try this with a linear fit as the simple example. So whenever this is the reason why spectrographs are so good, because you have more valent points, and your signal to noise is actually better than what your instrument is nominally telling you. You're here, you are easily interpreting the signals that are below your noise level. Magical, right? But the way I like to compare this with is that people do these observations of exoplanets. And these exoplanets, they have huge noise. But they do so many repeated observations that eventually they see this trend, they see the little dip, the little, how you call it, transit, right? And then they feed the transit and they find the parameters. So this is something like this. We can try with even higher noise. We can try with 2 times 10 to the minus 2 and see if it will break. Right, 2 to the minus 2. Right, a lot of noise. Still you see some trends. Let's save it. I don't know if I deleted the file. Let me delete the out file here. See if this works. I needed to restart my kernel because it died, because I opened too many things. Yeah, it's going to fit something. Takes a bit of time because there is very few valent points, and I artificially increase the number of iterations and strengthen the threshold for the convergence. It's gonna fit here. U and V. Trying to do something. Okay, did something. We open it, we plot. Finding something in this noise pattern. We plot the results. Even worse, Y, but kind of good still. Kind of good horizontal, vertical line of sight component. Could be X, could be Y. Always keep this in mind. Of course, I don't know if this will work in real life. Probably not, because in real life you have random noise and then systematic noise and all these things and etc. But sometimes you can see signals through just repeated measurements, so on and so on. Let's maybe have a quick Q&A session now. I can leave you to work here. I'm going to hang out here for a little while, but this is basically what I had for today. I hope that you understood basically what are the ingredients of these fits here, because tomorrow we're going to load up some real data. We're going to use it for our to start up these fits. So yeah, let's have some Q&A, and if you don't have any questions but you're interested to see something else, then maybe we can try and set up more complicated models and stuff like that.
So when we were doing cycles, we were doing first that we fit Stokes side, and once we fit everything else. Why don't we then have a third one where we fit all?
We can do that, sure. I disabled it in the meantime because sometimes it seems to mess up things. In this specific case, I changed it, but in principle, we can do that. Yeah, we can do that. Not, there are no really, how to say, hard rules in that sense. You're just trying to navigate through your chi-square surface and get to something that is good. Good question. Let's try and do that. Yeah, let's try and change that. For that, I think it's going to be much different because there is yeah. But let's change it. Let's put this to 90. Put this to 0. And here I'm going to say, let's say, and 5, 5. So these are the things. So we basically need few times. Okay, so my Q is really bad. Let me change the orientation a little bit. Maybe 2, 5, 5. But it's going to be bad. Let's say like this, 5. Oh, now this one sucks. Okay, let's see what I can. How do I orient so that this rotation is a bit smaller? So this is pointing. Okay, let's try like. Something like this. Okay, this is not terrible, right? This is roughly. Like you would say, we need like 10 to the minus 3 noise for this, roughly. Let's try and add 10 to the minus 3 noise, see what happens. Okay, it's a nonsense. Let's shrink it a little bit. So let's say 5 times 10 to the minus 4. Oh, no, this is now obviously good. Let's try. So this is. Let's do even more. Let's do 2 times 10 to the minus 3. The code can figure something out. Keep in mind, I need to change this one though. So this will be conf from, right? Conf test from. No, I cannot do it that way. Wait. I need to change all these ones here. So that I don't have to change the configuration file later. And here I also need to change this and this. Okay, there's a quite bit of this, but it's fine. Let's see if we can get it to work. Conf test from. No set conference from. This is only conf from. Conf from. Okay. Fine. Okay. This. Okay. Think something. Okay, it almost got very good fit. Well, it's very good fit because the noise is very small. So we're gonna see now if it it does something. Okay. Now, is it done? No, it's still working. I'll change this verbose to 2 for future. Okay, it's done. It's something. Now what happens? It's not that bad, honestly. Look. The uncertainty is huge. So here code is kind of finding reasonable uncertainty. Not that bad. Now, of course, the thing is that number of wavelengths is kind of doing, of course, I don't guarantee that this will change significantly. I expect it will. Now I have something like this. I run it like this. This inversion is going to be much faster now. I hope it is. I do a number of valence at some point. Getting some fit. Now the question is, of course, how that does make any sense? Okay. Okay, now it's nonsense, right? Now we could also like try to fit the original one over it. Let's try and do that. Also fit the, do I have unperturbed Stokes? Try and see if I didn't delete this one. One is fit nicely. I'm not surprised about that. Uh, 3, 2, 1. Wow. It's actually doing pretty good. How is it doing so good? What kind of sorcery is this? Maybe because my model is different. What is it? Maybe I overwrite, but it's not the file, it's the object, but maybe I did it. Yes. That's what I'm kind of skeptical about. Oh, but it's so sketchy. Is there a mod file here? Here's a model. Oh, yes, I did. Okay, so let's do something like this. Here we go and we say original, right? okay, it's not actually a terrible fit, right? The thing is, of course, that these small changes here are enough for us to get completely different magnetic field, because we are still, when we are in few Gauss, we're still in saturated Hanle regime, so it's still kinda. But yeah, these are not super terrible fits. For Stokes V, they kinda are. For QNU, not so much. Okay, more questions. Not, let me try and show you a trick real quick. What you could do is make code. Try and make this here, okay? We have stray light. So. I know, but we don't have the photosphere model. Okay. Okay, we can leave this for independent work. But here, if you go to basic usage on the help doc, then there is using the code. There is synthesis. It gives you options of combining multiple components. There you can have telluric lines, parametric, you have various kind of things. Combine them and you can get the profile. But that's now too much. But these are always interesting exercises for you to try and to see whether you will get back what you input, to kind of know and plan what kind of signal to noise you have. Another important thing that I want you to go through, definitely make sure that you went through this, is this previous one. So on this case, this got reset. Okay, fine. Let me go back and show it real quick. I won't invert, just to remind you. So this ambiguity section was the case. It wasn't even that bad, so the noise was kind of manageable. The same would have happened if I decrease the noise. It has nothing to do with that. Then when we fit this, we got these multiple solutions. We found these vectors that are like this. So if you ever plan, if you don't plan to use Hazel, you can just say, okay, it's fine. The ambiguous solutions exist. I need to know about this. We're done. But if you plan to use this, go through these motions. Go through the motions of calculating that, looking at the chi-square, eliminating bad chi-squares from the multiple randomizations, and then visualizing these, and if possible, even projecting them to your own line of sight. Right? More questions? If not, we can stop here. So tomorrow, I will upload a new exercise notebook for tomorrow. In the first notebook, we're going to go through some individual profiles. In the second one, we're going to look through a data set. And there we're also going to do a little bit of, inspection first to see what hides in that data set. And then we can fit individual profiles if you feel like it. It's nothing complicated. It's Zeeman on disk, so it's very straightforward to fit. But what will be interesting is that I will add some files for you that are preparing that data for inversion, so that you can literally just run 3 commands in your terminal and you have it ready. Okay. Good. Well, in that case, we're done for now. I'm gonna hang around here for like half an hour more, just because I'm waiting for some people to pick me up. If you have some questions, don't hesitate to ask, and see you tomorrow at 8:30.